The universe is a massive place filled with countless wonders and mysteries. From immense clusters of galaxies stretching across hundreds of millions of light-years to the faint glow of ancient radiation, it extends far beyond what we can easily imagine. There are billions of galaxies, each containing billions of stars, and around many of those stars, planets circle in quiet, unending orbits. In this vast ocean of space, our Earth is a tiny, almost invisible speck, a small world drifting through the darkness. Yet within that small world, everything we know and everything we are has unfolded. Every landscape we have walked, every breath we have taken, and every story we have told has taken place on the surface of this single planet. Earth is one planet among countless others that may exist in the universe, orbiting an ordinary star in an ordinary part of our galaxy, and in these ways it seems unremarkable. At the same time, it is extraordinary to us because it is the place that holds all known life, the one environment where life as we know it has taken root and flourished. In this series, we will move slowly and carefully through this idea of home. Join us as we embark on a journey that is meant to be gentle and unhurried, a quiet exploration that you can listen to while you rest, relax, or drift towards sleep. Our pace will follow the calm rhythm of orbits and tides rather than the rush of daily life, returning again and again to the simple fact that we are residents of a planet traveling through space. The goal is not only to share information, but to create a space where the mind can wander safely among the wonders of the cosmos. To do this, we will often zoom out and then back in, shifting from the grand scale of galaxies and gravity to the intimate scale of oceans, forests, and the thin layer of air that surrounds us. From the outside, Earth is a sphere of rock and water wrapped in a delicate atmosphere, illuminated by the sun and shielded by an invisible magnetic field. From the inside, it is the ground beneath our feet, the sky above our heads, and the familiar pull that keeps us anchored while our planet races through space at tremendous speed. For now, imagine yourself floating far from home, suspended in the quiet of deep space. Around you, stars shine in every direction, forming the hazy band of our Milky Way galaxy. As we begin, we will slowly draw closer, first to our solar system, then to the orbit of our own planet, and finally to the living surface of Earth itself, a testament to the dynamic and transformative processes of the cosmos and the place we call home. From that distant vantage point, we can now begin to trace our true location, building what astronomers sometimes call our cosmic address, step by gentle step. Join us as we embark on a journey inward, from the grand sweep of galaxies and stars to the quiet room where you are listening now, and notice how each level nests inside the next like a set of cosmic shells. At the smallest scale of this address is your immediate space, the room, the bed or chair, the familiar objects within arm's reach. Here, distances are measured in centimeters and meters, and gravity simply feels like down. Yet even in this calm environment, you are already moving with Earth's rotation, carried eastward at hundreds of meters per second, though everything appears still. Beyond your walls lies your city and country, a thin patchwork of lights, roads and landscapes spread over the surface of a sphere about 12,700 kilometers across. From tiny particles to massive continents, almost everything you experience takes place in a layer of air and water only a few kilometers thick. the biosphere, where life as we know it clings to the boundary between rock below and sky above. Earth, our shared planet, orbits the Sun at about 30 kilometers per second, completing one circuit each year. The Sun, a medium-sized star, sits at the heart of our solar system, and the space between planets is vast. If Earth were the size of a marble, the Moon would be a pea a few centimeters away, but Mars would already be across the room, and Neptune would be far down the street. In these ways, we begin to sense how much emptiness surrounds the small islands of solid ground we call home. Our solar system itself is only a tiny neighborhood inside the Milky Way galaxy, a rotating disk about 100,000 light-years across, containing hundreds of billions of stars and their planets. We orbit the galactic center at roughly 220 kilometers per second, so that, when combined with Earth's spin and orbit, our actual speed through space exceeds 1,000,000 miles per hour. Yet the floor beneath you feels steady and unmoving. Beyond the Milky Way, our address expands again into clusters and filaments of galaxies, and finally into the observable universe, a sphere nearly 46 billion light-years in radius, filled with perhaps 2 trillion galaxies. Most of this vast cosmos is cold, airless, and hostile to complex organisms, a testament to the dynamic and transformative processes of the cosmos that shaped rare pockets where conditions are just right. Within this immensity, Earth offers a remarkably stable-feeling refuge, a protective atmosphere, a magnetic field deflecting harmful solar particles, and plate tectonics that help regulate climate over billions of years. Understanding our place in this hierarchy of scales can deepen our appreciation of our planet as an unusually gentle harbor in a largely harsh universe, and it prepares us to look more closely at how Earth itself formed, evolved, and continues to support the delicate patterns of life spread across its surface. In this gentle harbor, something remarkable is happening all the time, whether we notice it or not. While we stand on solid ground, watch the sky, or drift towards sleep, our entire world is in motion, tracing an intricate path through the universe that is both dizzying in speed and soothing in its regularity. Earth, our home planet, orbits the Sun at about 30 kilometers per second, a steady rush that carries us around our star once every year, and sets the rhythm of our seasons and much of life as we know it. From tiny grains of dust in the early solar system to fully formed planets, this orbital dance is a testament to the dynamic and transformative processes of the cosmos. And yet, we feel no wind from this motion, no tug that reminds us we are circling a star. From our orbit around the Sun to the broader journey of the solar system through the Milky Way, the scales of motion expand dramatically. The entire solar system, with its planets, moons, and smaller bodies, orbits the center of our galaxy at roughly 220 kilometers per second, taking about 230 million years to complete a single galactic year. Beyond that, the Milky Way itself moves through space relative to the faint afterglow of the Big Bang, the cosmic microwave background, so that when these motions are combined, Earth is traveling at over 1,000,000 miles per hour through the larger universe. This immense speed raises a quiet question. Why do we feel so still? The answer lies in inertia and reference frames, the simple but profound ideas that when motion is smooth and constant, everything around us shares that motion, so we experience it as rest. When we sit inside a calm airplane at cruising altitude or ride a smooth train, we can walk, read, or sleep without sensing the hundreds of miles per hour beneath us. And in these ways, our daily lives on Earth are like a long, unbroken flight through space. The air we breathe, the oceans and continents, our cities and forests, all share Earth's motion, so there is no sudden jolt to betray our true speed, only the slow turning of the sky and the familiar cycle of day and night. Join us as we embark on a journey through this perspective, where every sunrise is the edge of our orbit sweeping into light, and every quiet night is a moment on a vast galactic path traced among the stars. Seen like this, even the most ordinary landscape becomes part of a grand voyage through galaxies and intergalactic space, powered by gravity and the stored energy of ancient cosmic events. To understand how Earth can carry us so safely on this ceaseless journey, we now need to look back in time, to the violent cloud of gas and dust from which our planet emerged, and to the hidden structures that make it stable, habitable, and perhaps more fragile than it first appears. The solid world that carries us through the universe did not begin as solid at all. To trace Earth back to its origins, we have to leave this calm, stable surface and return to a time before there were planets, before there was even a sun, when everything we now know was part of a dark, drifting cloud in space. Over 4.5 billion years ago, our region of the galaxy was occupied by a vast molecular cloud, a cold and tenuous mixture of gas and dust stretching for light years. This cloud, rich in hydrogen and helium with traces of heavier elements forged in earlier generations of stars, was not yet a solar system, but it held the raw material for one. At some point, perhaps triggered by the shock wave of a nearby supernova, part of this cloud was disturbed and compressed, and that gentle nudge was enough for gravity to begin its slow, relentless work. As gravity pulled matter inward, the collapsing region of the cloud spun faster, just as an ice skater spins more quickly when drawing in their arms. The result was a flattened, rotating protoplanetary disk surrounding a growing protostar at its center, the young object that would become our Sun. Within this disk, temperatures and densities varied from the hot inner regions to the colder outskirts, setting the stage for different kinds of planets to form, from rocky worlds like Earth to the giant planets farther out in the solar system. Inside this disk, the process of planet formation began with the smallest of building blocks. Tiny dust grains coated with ices and minerals started to collide and stick together, at first through weak electrostatic forces and later through their own increasing gravity. These grains grew into pebbles, then boulders, and eventually into kilometer-scale planetesimals, solid bodies massive enough to attract more material. The early solar system was a chaotic environment, filled with frequent and often violent impacts as these planetesimals merged into larger protoplanets, their surfaces constantly reshaped by collisions that released enormous amounts of energy. Earth emerged from this turbulent phase as one of those protoplanets, initially a molten and partially vaporized world. In this global ocean of magma, heavy elements such as iron and nickel sank inward under the pull of gravity, forming a dense core, while lighter silicate materials floated upward to create a primitive mantle and crust. In these ways, the layered interior of our planet was established, a testament to the dynamic and transformative processes of the cosmos that continue to influence Earth's behavior today. When we stand on what feels like unchanging, solid ground, we are touching the final, cooled skin of the long history of collapse, collision, and differentiation. The continents and ocean basins beneath our feet are the quiet outcome of billions of years of cosmic energy being redistributed and stored. Join us as we embark on a journey from this hardened surface down into Earth's hidden interior, where heat still flows, rock slowly moves, and the conditions that allow life as we know it are maintained by processes we rarely see but constantly depend upon. Yet even before Earth's interior settled into layers and slow currents of rock, a single, extraordinary event reshaped our young world and set the stage for the conditions we now depend on. In the early solar system, when planets were still forming from a swirling disk of gas and dust, Earth did not travel alone along its orbit around the Sun. The leading idea, known as the giant impact hypothesis, suggests that a Mars-sized body, which scientists call Theia, shared our path and eventually crossed it in a catastrophic glancing collision. The universe, from tiny particles to massive galaxies, builds structure through gravity and impact, and this was one of the defining blows in Earth's history. Theia struck with immense energy, melting rock, vaporizing crust, and briefly turning much of the surface into a global ocean of magma. From this violence came an unexpected kind of order. The collision ejected vast amounts of molten and vaporized rock into orbit, forming a glowing temporary ring of debris around the damaged Earth. Over time, guided by gravity, this material clumped together fragment by fragment until it coalesced into a single large body, the Moon. Below, Earth itself reformed from the remaining material, its rotation altered, its tilt adjusted, its interior further stirred by the impact's heat. The Moon, a silent companion in our night sky, became a stabilizing influence almost immediately. Earth's axis, the imaginary line around which we spin, is tilted relative to our orbit, and this tilt creates our seasons. Without the Moon's steady gravitational pull, that tilt would likely wander far more over millions of years, producing extreme and chaotic climate swings. With the Moon, the tilt remains within a narrower range, and in these ways, our planet has enjoyed relatively stable seasons over geological time, a quiet backdrop against which life as we know it could emerge and adapt. The influence of the Moon also reaches into the oceans. Its gravity pulls on Earth's seas, creating the rhythmic rise and fall of tides that move vast amounts of water and energy across the coasts each day. In the deep past, these tides would have repeatedly flooded and exposed shorelines, tidal flats and shallow pools, concentrating minerals and organic molecules, and perhaps helping early chemistry bridge the gap toward biology. The gentle but persistent tug of our satellite may have shaped habitats where the first coastal ecosystems evolved. When we look up and see the Moon, we are not just seeing a distant sphere of rock, we are seeing a testament to the dynamic and transformative processes of the cosmos. This world, born from collision, has acted as a crucial collaborator, calming Earth's spin, guiding its waters, and making our planet a more predictable and habitable home. As we continue our journey through Earth's story, we will see how this partnership interacts with the atmosphere, the oceans, and the deep interior to sustain a living world, orbiting an ordinary star in a vast universe of wonders of the cosmos. That calm, predictable partnership between Earth and the Moon rests on a planet that is anything but simple inside. From the solid ground beneath our feet to the invisible shield that guards us from space weather, our homeworld is built as a layered sphere, shaped from the inside out, Join us as we embark on a journey beneath the surface, into regions no human has ever seen, yet that quietly sustain life as we know it. Earth, a rocky planet in our solar system, is divided into four main internal layers: the crust, mantle, outer core, and inner core. The crust is the thin, brittle skin of solid rock where continents, oceans, and the entire biosphere reside, a delicate film compared to the planet's full radius. Beneath it lies the mantle, a vast region of hot, high-pressure silicate rock that behaves as a very slow, deformable solid. Deeper still, we find the outer core, a sea of liquid metal, and at the very center, the inner core, a solid sphere dominated by iron. This structure is not accidental. It is a testament to the dynamic and transformative processes of the cosmos. Early in Earth's history, when collisions and radioactive decay filled the young planet with intense energy, the interior partially melted. In that molten state, gravity sorted the ingredients by density in a process called differentiation. Heavy elements such as iron and nickel sank inward to form the core, while lighter silicate minerals floated upward, cooling and solidifying into the mantle and, eventually, the crust. In these ways, a chaotic, glowing sphere of mixed material became a stratified world with distinct layers and long-term stability. The mantle, though solid on human timescales, slowly convects over millions of years, with hotter, buoyant rock rising and cooler, denser rock sinking back toward the core. This churning motion acts as a deep engine, transferring heat outward and driving plate tectonics at the surface. From mountain building and earthquakes to volcanic eruptions that release gases and nutrients, the mantle's flow continuously reshapes continents and seafloor. Over geological ages, this restless activity helps regulate climate by cycling carbon between rocks, oceans, and the atmosphere, keeping liquid water stable over billions of years. Around the mantle, the liquid outer core of iron and nickel behaves like a vast, electrically conducting ocean. As it circulates and shears around the solid inner core, this moving metal generates Earth's magnetic field through the geodynamo process. The field extends tens of thousands of kilometers into space, deflecting much of the charged particle stream from the sun and helping to prevent the atmosphere from being stripped away. Without this shield, our planet might resemble Mars, with a thin sky and a surface exposed to harsh radiation. Everyday stability on Earth, from reliable ground to a temperate climate and a protective magnetic cocoon, is rooted in these hidden depths. The quiet soil under a forest, the steady pull of a compass needle, and the gentle filtering of solar radiation all depend on processes unfolding thousands of kilometers below us. As we look outward to other planets and distant galaxies, we will see how rare it may be for a world's interior and surface to align so delicately, sustaining a long-lived habitable environment in a universe filled with extremes. The universe may seem distant and abstract when we look up at the night sky, yet one of its most subtle and powerful structures is wrapped directly around us, shaping the air we breathe and the conditions that allow life as we know it to endure. Join us as we embark on a journey not outward to distant galaxies this time, but inward and upward into an invisible shield that quietly guards our world. Surrounding Earth is a vast magnetic envelope, the magnetosphere, an immense bubble carved into space by our planet's magnetic field. From tiny particles to massive streams of solar energy, This bubble extends tens of thousands of kilometers into space, stretching far beyond the atmosphere and even beyond the orbit of many satellites. On the day side, it is compressed by the solar wind into a rounded shell, while on the night side it is drawn out into a long magnetic tail, a dynamic, shifting cocoon that responds constantly to the sun's changing mood. This protective field arises from deep within Earth, far below the solid crust and the slowly flowing mantle, in a realm we will never visit directly. There, in the outer core, molten iron and nickel churn in convective motion, rising and sinking under the influence of heat escaping from the planet's formation, and the solid inner core. As Earth rotates, this electrically conducting ocean of metal is twisted and organized, and in these ways, moving charges create a global magnetic field, a self-sustaining geodynamo that has persisted for billions of years, a testament to the dynamic and transformative processes of the cosmos. The magnetosphere acts as a giant deflector, turning aside most of the solar wind, a continuous stream of charged particles flowing outward from the sun. Without this shield, these particles would slam directly into the upper atmosphere, transferring energy, knocking atoms into space, and gradually eroding the very gases that regulate climate and allow liquid water to remain stable on the surface. We still see beautiful auroras when some particles spiral down magnetic field lines near the poles, but the bulk of this solar assault is diverted, reshaped into gentle displays instead of long-term atmospheric loss. We can see the importance of this magnetic cocoon by comparing Earth to Mars, another rocky planet in our solar system that once hosted flowing water on its surface. Evidence suggests that Mars lost most of its global magnetic field early in its history, leaving its atmosphere exposed to the full force of the solar wind. Over hundreds of millions of years, much of that atmosphere was stripped away, leaving a cold, thin-air environment where liquid water is unstable at the surface, and any potential biosphere must retreat underground. As we rest under our own sky, it is easy to forget that every breath we take depends indirectly on this hidden engine of molten metal. For a moment, imagine that beneath your feet lies a vast, silent ocean of liquid iron, slowly turning under the pull of gravity and rotation, generating an invisible shield that holds the air close, softens the sun's harsher energies, and helps keep Earth a rare blue oasis in a universe filled with extremes. That invisible shield does more than guard us from charged particles. It also helps hold close a second, even more delicate protector, a film of gas so thin that, on the scale of the whole planet, it is almost nothing at all. If Earth were the size of a basketball, the atmosphere that makes it feel like home would be thinner than a coat of paint. Yet within this fragile envelope, almost everything we have ever experienced takes place. From tiny insects gliding just above the ground, to jets cruising high overhead, from gentle breezes to towering storm clouds, we live immersed in this thin blue veil, a mixture of gases that moderates temperature, shields us from harmful radiation, and fills our lungs with the oxygen that sustains life as we know it. Without it, days would scorch, nights would plunge toward the deep cold of space, and liquid water would be rare or impossible on the surface. The atmosphere, like the planet itself, has a history written in fire and ice. In its earliest days, Earth, still young and reshaped by constant impacts, released vast amounts of gas from its hot interior, a process called volcanic outgassing, filling the sky with water vapor, carbon dioxide, nitrogen, and traces of other compounds. Comets and icy bodies from the outer regions of the solar system likely added more water and volatile materials, delivering impact by impact the raw ingredients for oceans and air. Over time, as the planet cooled and oceans condensed from the thick, steam-filled air, a new player emerged: biology. Primitive photosynthetic organisms in the sea began using sunlight as an energy source, taking in carbon dioxide and releasing oxygen as a byproduct, slowly transforming a suffocating atmosphere into one where complex, oxygen-breathing life could thrive. In these ways, the sky above us is a testament to the dynamic and transformative processes of the cosmos, linking volcanic rock, icy visitors, and microscopic life into a single long story. Today, we divide this story-rich shell into distinct layers. Closest to the ground is the troposphere, the lowest region where almost all of our weather occurs and where we spend our entire lives, stretching only about 10 to 15 kilometers up. Above it lies the stratosphere, calmer and more layered, home to the ozone layer, a region enriched in a special form of oxygen that absorbs much of the sun's ultraviolet radiation before it can damage DNA and disrupt ecosystems at the surface. Higher still, the mesosphere and thermosphere extend outward into space, thin and rarefied, where temperatures can soar in response to absorbed solar energy even as the few atoms present are far apart. These upper layers interact with the solar wind and the magnetic field, helping to dissipate incoming energy and giving rise to auroras, shimmering curtains of light that remind us of the constant exchange between our planet and the wider universe. Threaded through all of these layers are greenhouse gases, molecules like carbon dioxide, water vapor, and methane, present in small amounts yet exerting a powerful influence. They allow much of the sun's visible light to reach the surface, where it warms land and oceans, then absorbs some of the outgoing infrared radiation, gently trapping heat and keeping Earth's average temperature in the narrow range where liquid water can persist over billions of years. Without this natural greenhouse effect, global temperatures would drop far below freezing, and our blue oceans might be locked in ice. When we step back, we see that over 99.9% of Earth's volume is uninhabitable to us. We cling instead to a narrow band only a few kilometers above and below the surface, a thin biosphere suspended within an even thinner atmosphere. Join us as we embark on a journey from this fragile shell of air out into the broader architecture of Earth's systems, where oceans, rocks, ice, and living things intertwine to keep our planet stable amid the vast, changing wonders of the cosmos. From this fragile shell of air wrapped around rock and water, we can step back in our minds and see Earth as one planet among many, circling an ordinary star in a vast universe filled with galaxies and uncounted worlds. Yet when we compare our home to its nearest neighbors, we discover that Earth occupies a surprisingly narrow band of conditions, a slender zone where temperatures and pressures allow liquid water to persist on the surface and where life as we know it can endure for billions of years. Astronomers call this band the habitable zone, the region around a star where, given the right kind of atmosphere, a planet's surface can maintain water in liquid form, rather than locked as ice or boiled into steam. It is not a hard-edged ring, but a range that depends on the star's brightness and the planet's ability to trap or shed heat. In these ways, the concept is simple, yet the reality is subtle, because distance from the sun is only the first step in a long chain of requirements that must all align to keep a world clement instead of hostile. We can see this clearly when we look inward to Venus, Earth's so-called sister planet, almost the same size and bulk composition, formed from the same cloud of material in the early solar system. Venus orbits only a bit closer to the sun, receiving roughly twice the solar energy that Earth does, but its thick carbon dioxide atmosphere, over 90 times denser than ours, has driven a runaway greenhouse effect. Sunlight pours in, heat is trapped, and with almost no way to radiate that energy back to space, the surface bakes at about 460 degrees Celsius, hot enough to melt lead and erase any liquid oceans that might once have existed. Outward from Earth, Mars offers the opposite lesson, a smaller rocky planet that almost certainly once hosted rivers, lakes, and perhaps even a northern ocean, but which now lies cold and largely dry beneath a thin veil of air. With only a fraction of Earth's mass, Mars could not hold a thick atmosphere against the constant erosion of the solar wind, especially without a long-lived global magnetic field, and its weak greenhouse effect leaves average surface temperatures far below freezing. Any remaining water is mostly locked away as ice in polar caps and buried beneath dust and rock. Earth sits between these extremes, and its long-term habitability arises from a careful balance of distance, atmosphere, and internal activity. Our orbit places us where sunlight is strong enough to prevent a permanent global deep freeze, yet not so intense that oceans simply boil away, while our atmosphere, with its mix of nitrogen, oxygen, water vapor, and modest amounts of greenhouse gases like carbon dioxide, traps just enough heat to smooth daily and seasonal swings. Deep inside, Earth's active geology and plate tectonics slowly cycle carbon between rocks, oceans, and air, stabilizing climate over millions of years and keeping liquid water on the surface despite changes in the sun's output. This balance, however, is not guaranteed forever. It is maintained by slow, powerful planetary systems, climate feedbacks, interior cooling, orbital variations that we are only beginning to understand in detail. Join us as we embark on a journey into these regulating mechanisms, a testament to the dynamic and transformative processes of the cosmos that have kept our world temperate so far, and that will shape the future habitability of the only planet we currently know that harbors life. Those regulating mechanisms do not act in isolation. They are woven together by one substance that quietly dominates the surface of our world. From the vantage point of space, Earth appears as a blue planet, its continents framed by swirling white clouds and vast, dark basins of ocean. Join us as we embark on a journey across these global seas, because they are not just scenery, they are the defining feature that makes our planet unlike any other we currently know in the universe. Earth is so far the only known planet with immense, stable oceans of liquid water exposed directly to space, covering about 71% of its surface in a single, interconnected global system. Other planets and moons in our solar system may hide subsurface oceans or preserve water as ice and vapor, but only here does liquid water pool in basins thousands of kilometers wide, interacting continuously with atmosphere, land, and life. In these ways, the oceans turn what would be a dry rock under the sun into a living, breathing world. Water itself, a simple molecule of hydrogen and oxygen, possesses a remarkable suite of physical properties that make it uniquely suited to regulate climate and support complex chemistry. Its high heat capacity allows the oceans to absorb and store vast amounts of solar energy without extreme temperature swings, smoothing out seasons and moderating coastal climates so that winters are milder and summers cooler than they would otherwise be. At the same time, water is an exceptional solvent, dissolving salts, gases, and organic molecules, enabling the intricate reactions that underpin life as we know it, from the metabolism inside a single cell to the global cycling of carbon and nutrients. Above these oceans, the water cycle operates as a planetary engine, lifting molecules from sea to sky and returning them again in a continuous loop. Warmed by sunlight, surface waters evaporate, carrying latent energy into the atmosphere, where rising air cools and water condenses into droplets and ice crystals, forming clouds that drift with the winds. Eventually, this condensed water falls back as rain or snow, feeding rivers, glaciers, and groundwater, before running off through valleys and deltas to rejoin the sea. This ceaseless circulation links ocean, atmosphere, and land into a single Earth system, a testament to the dynamic and transformative processes of the cosmos playing out on a human scale. Within the oceans themselves, currents act as conveyor belts of heat and salt, redistributing energy from the equator toward the poles and from surface layers into the deep. Surface currents driven by winds, like the Gulf Stream, carry warm water along continental margins, softening climates in regions that would otherwise be far colder at their latitude, while deeper thermohaline circulation slowly overturns the ocean on thousand-year timescales, influencing patterns of ice, storms, and even the strength of monsoons. From tiny ripples to basin-spanning gyres, these flows shape weather systems that can affect continents at once. The story of life on Earth is, in many respects, the story of water. The earliest microbial ecosystems almost certainly arose in liquid water, perhaps in sunlit surface layers or around mineral-rich hydrothermal vents on the young ocean floor, where chemical gradients provided the energy needed to drive the first primitive metabolisms. Even today, the majority of Earth's biomass and a large fraction of its biodiversity may reside in marine environments, from dense phytoplankton blooms that feed entire food webs to the hidden communities of the deep sea, living in perpetual darkness beneath crushing pressure. From tiny drifting organisms that help set the composition of our atmosphere to great whales that migrate across entire ocean basins, marine life participates in global cycles of carbon, oxygen, and nutrients that help stabilize the climate we depend on. From this perspective, our familiar landscapes of forest, desert, and city are perched on the margins of a water world, their fate tightly bound to the state of the seas. The oceans buffer changes, but they are not infinitely forgiving. And as we alter the atmosphere and warm the surface, currents, chemistry, and ecosystems respond in ways we are only beginning to trace. In the next part of our journey, we will leave the rolling surface of these global oceans and descend inward into the solid planet beneath, where slow motions of rock and hidden reservoirs of water and heat shape the continents themselves in ways that may ultimately decide how long our blue world remains habitable. Beneath the oceans and continents we see each day, Earth hides a slower, deeper kind of motion, one that quietly reshapes the surface over tens of millions of years. Join us as we embark on a journey into this restless, solid world, where rock behaves almost like a very cold, very stiff fluid, and where the ground under our feet is not as fixed as it seems. The outer shell of our planet, the lithosphere, is broken into rigid plates that drift across a softer, convecting layer beneath. The asthenosphere, driven by heat left from Earth's formation and by the decay of radioactive elements. From tiny minerals to whole continents, this slow overturning of rock is a testament to the dynamic and transformative processes of the cosmos, showing us that even solid planets are never truly still. Where these plates move apart at divergent boundaries, new crust is created as molten rock, wells up, freezes, and pushes older seafloor aside, forming mid-ocean ridges that circle the globe like seams on a baseball. Where plates collide at convergent boundaries, one plate may dive beneath another in subduction zones, feeding deep ocean trenches and building mountain ranges such as the Andes and the Himalaya. Sliding past each other along transform boundaries, plates grind and lock, storing elastic energy that is suddenly released in earthquakes when frictional resistance fails. These shifting plates do more than sculpt mountains and basins. Over geological time, they help run a planetary thermostat. When rainwater, slightly acidic with dissolved carbon dioxide from the air, falls on fresh rock uplifted by tectonics, it slowly weathers minerals, locking carbon into dissolved ions that rivers carry to the oceans. There, this carbon becomes part of carbonate sediments and shells, which accumulate on the seafloor, forming thick layers of rock rich in carbon and calcium. As plates continue to move, some of this seafloor is dragged down at subduction zones, carrying carbon-bearing rocks into the deep interior, where high temperatures and pressures release part of that carbon again. Volcanic arcs above subduction zones and hotspots elsewhere return this carbon dioxide to the atmosphere through eruptions and diffuse degassing, closing what we call the carbon silicate cycle and linking the deep earth to the air we breathe. In these ways, over millions to hundreds of millions of years, plate tectonics help stabilize the amount of carbon dioxide in the atmosphere, buffering swings between icehouse and greenhouse states, and keeping conditions suitable for liquid water and for life as we know it, even as the sun's energy output slowly increases. Planets without this slow recycling, like Mars with its thick, immobile crust, or Venus with its stagnant lid and overwhelming greenhouse blanket, offer a contrast that may be sobering. Without a living, shifting surface, long-term climate regulation may fail. From our place in the solar system to the broader universe of rocky planets around distant stars, Earth's mobile crust may be unusually favorable, perhaps even rare, in supporting billions of years of oceans and biospheres. As we turn next to the deep interior, we will see how hidden reservoirs of heat, metal, and motion sustain this tectonic engine and help shield our fragile surface world from the harsher radiation of space. Deep beneath the drifting plates and circulating mantle, another global system has been quietly shaping Earth's surface and climate for billions of years. It is as if the planet itself breathes, trading invisible gases between air, oceans, rocks, and living things, maintaining conditions that have allowed oceans, continents, and life as we know it to endure across deep time. This planetary breath is the carbon cycle, a vast network of reservoirs and pathways that moves carbon atoms from place to place. In the atmosphere, carbon appears mainly as carbon dioxide, a trace gas that nonetheless plays an outsized role in trapping heat and regulating climate. The oceans absorb and release this CO2, dissolving it into seawater, where it can form bicarbonate and carbonate ions, or be taken up by drifting plankton. On land, carbon is stored in forests and grasslands, in soils rich with decaying leaves and roots, and, over even longer spans, in sediments and solid rocks that lock it away for millions of years. At the surface, biology drives some of the fastest and most familiar exchanges. Through photosynthesis, green plants on land and microscopic algae in the sea pull carbon dioxide from the air and water, using the sun's energy to build sugars and other organic molecules. In these ways, carbon becomes the backbone of biomass, the substance of leaves, trunks, and living cells. When organisms respire, they reverse part of this process, breaking those molecules down to release energy, water, and CO2 back to the environment. When they die, decomposers in soils and sediments continue the work, so that, on human timescales, a dynamic balance emerges between carbon stored in living matter and carbon returned to the air. Over far longer intervals, chemistry and rock formation take the lead. Rainwater, slightly acidic because it contains dissolved CO2 from the atmosphere, seeps into cracks and pores, reacting with silicate minerals in continental rocks. This chemical weathering slowly consumes carbon dioxide, carrying it away in rivers as dissolved ions that eventually reach the oceans. There, marine organisms use some of these ions to build shells of calcium carbonate, which, when they die, settle to the seafloor and accumulate as layers of sediment. With burial and time, these layers harden into limestone and other carbonate rocks, while in oxygen-poor environments, buried organic matter can be transformed into coal, oil, and natural gas. Plate tectonics then closes the loop on planetary scales. As oceanic plates descend back into the mantle at subduction zones, they carry carbonate sediments and altered crustal rocks downward, returning stored carbon to Earth's interior. Some of this carbon is later released through volcanic eruptions and diffuse degassing, emerging again as CO2 at the surface. From tiny reactions in raindrops to towering volcanic plumes, the whole system acts as a long-term thermostat, a testament to the dynamic and transformative processes of the cosmos that has helped keep Earth's climate within a relatively stable range, even as the sun's energy output has slowly increased. There is a quiet pattern interrupting this ancient rhythm. In just a few centuries, human societies have begun tapping those deep fossil carbon stores and altering forests and soils, injecting CO2 into the atmosphere far faster than most natural processes can remove it. We will explore these changes later, but for now, it is enough to recognize that our species has become part of the carbon and climate engine itself. Join us as we embark on a journey inward to see how Earth's atmosphere and oceans respond to this shifting balance, and how a thin, fragile film of air can mediate the flow of energy between our planet and the wider universe. The universe is a massive place filled with countless wonders and mysteries, yet for us, everything that truly matters is confined to an almost unimaginably thin layer on the surface of one small planet. As we shift our attention from swirling clouds of gas and global circulation patterns, we arrive at the biosphere, the delicate skin of Earth where life as we know it can exist at all. The biosphere, in scientific terms, is the sum of all regions where life is found, a continuous but fragile shell that wraps around our world. It extends only a few kilometers into the atmosphere, where microbes and insects can ride air currents and where birds trace their paths beneath the clouds, and only a few kilometers into the crust and the deep oceans where roots, burrowing animals and strange microbial communities occupy tiny fractures and sediments. Above this narrow band, the air becomes too thin, too cold, and too irradiated, while below it, pressure and temperature rise into realms that crush or cook complex organisms. From tiny soil bacteria to towering forests, from coral reefs glowing in shallow tropical seas to dark, high-pressure trenches in the abyss, almost all known life is confined to this narrow zone. Over 99.9% of Earth's volume lies outside it, uninhabitable to humans and hostile to most organisms, a reminder that our living world is not the whole planet, but a film upon its surface. In these ways, Earth resembles a vast, solid sphere, wrapped in a breathing membrane, with nearly all the chemistry of living cells, all the exchange of oxygen and carbon, and all the intricate food webs taking place in a layer that is almost vanishingly small compared to the globe beneath. To picture just how thin this layer is, it can help to turn to a simple analogy. If Earth were shrunk down to the size of a basketball, the entire biosphere, from the highest drifting microbes in the upper air to the deepest known ecosystems around hydrothermal vents, would be thinner than a coat of paint on its surface. The mountains, the oceans, the forests and cities, all the habitats we can easily imagine, would merge into a glossy sheen that you could almost wipe away with a cloth. Within that paint-like film, however, diversity flourishes. Around deep-sea vents where sunlight never reaches, chemosynthetic organisms draw energy from mineral-rich fluids rising from Earth's interior, building ecosystems that depend on geology rather than starlight. High in the atmosphere, bacterial cells and fungal spores ride droplets and ice crystals, forming tiny transient communities in cloud layers that drift above continents and oceans. On the seafloor, in polar ice, in desert crusts, and even kilometers underground in water-filled rock pores, life has adapted to extremes of pressure, temperature, salinity, and scarcity, a testament to the dynamic and transformative processes of the cosmos that forged both our planet and the molecules that make living systems possible. Every person you have ever met, every structure ever built, every memory ever formed in a human brain has unfolded entirely within this fragile film. Our civilizations, our stories, and our technologies are all surface phenomena, dependent on a narrow balance of temperature, atmospheric composition, and liquid water that the biosphere helps to maintain. Join us as we embark on a journey to see how this living layer interacts with rock, air, and ocean, and how the larger Earth system works to support, and sometimes to threaten, the continuity of life on this small world orbiting an ordinary star. The living skin of Earth does not only depend on temperature and chemistry, it also depends on the quiet, ceaseless turning of the planet itself. While we feel still and rooted to the ground, we are in fact riding a world that spins once on its axis in roughly 24 hours, carrying every ocean, continent, and cloud from daylight into darkness and back again in a continual cycle that has persisted for billions of years. This daily rotation, the steady spinning of Earth around an imaginary line running from the North Pole to the South Pole, is what creates the alternation of day and night that feels so familiar and predictable. From tiny particles to massive galaxies, motion is a universal theme, and our planet is no exception, rotating at about 1,600 kilometers per hour at the equator, yet held together by gravity so that we experience only the slow drift of the sun across the sky, the lengthening of shadows, and the deepening of twilight as direct sunlight fades and our region of the planet turns away from our star. Earth's rotation also leaves a subtle but profound imprint on the air and the sea. Because different latitudes move at different speeds, anything that travels long distances over the surface, winds, ocean currents, even flight paths, experiences a gentle sideways deflection known as the Coriolis effect, a consequence of the rotating frame of reference. In these ways, broad belts of winds form. Trade winds blow towards the equator, and great ocean gyres slowly swirl within each basin, redistributing heat, moisture, and energy, and helping to shape the climate patterns that make life, as we know it, possible on this particular planet in the solar system. Living organisms have not simply endured this rhythm, they have woven it into their biology. Most complex life on Earth, from single-celled algae to trees, insects, birds, and humans, carries internal timekeepers called circadian rhythms, biochemical clocks that run on a cycle of about 1 day. These rhythms synchronize to the light-dark pattern imposed by rotation, regulating when we sleep and wake, when plants open their leaves or flowers, and when nocturnal animals emerge to feed, so that behavior, metabolism, and even gene activity rise and fall in tune with the turning of the planet. For human cultures, the regularity of sunrise and sunset has long been a guide and a measure. Ancient observers watched the shadow of a stick sweep across the ground. Built stone circles aligned to the first light of particular days, and divided the rotation into hours, minutes, and seconds, creating formal timekeeping that coordinates modern societies. Farmers have planted and harvested by the length of the day. Navigators once steered ships by the stars as they wheeled overhead. And even in our illuminated cities, we still feel the pull of morning and evening as Earth continues its silent spin. This daily dance is only one layer of a larger choreography. Join us as we embark on a journey from the swift rotation that gives us day and night to the slower orbit that traces our path around the sun, and onward to the grander cycles that connect our small world to the wider patterns of the universe, a testament to the dynamic and transformative processes of the cosmos that have shaped Earth into the home we know. As Earth spins and circles the sun, it does something quietly remarkable. It leans. This lean or axial tilt is only about 23.5 degrees, yet it reshapes the flow of sunlight across our world and turns a simple orbit into a rich rhythm of change. From this modest angle arises the pattern of seasons that structures so much of life as we know it. The axis of Earth, an imaginary line running from the North Pole to the South Pole, does not stand upright relative to our orbit. Instead, it is tipped, so that during different parts of the year one hemisphere is inclined toward the sun, while the other is inclined away. When the northern hemisphere tilts sunward, sunlight arrives more directly. Days lengthen, and the familiar warmth of summer spreads across continents, while the southern hemisphere receives lower angle light, shorter days, and the cooler conditions of winter. Months later, as we move to the opposite side of our nearly circular orbit, this situation reverses, and the balance of light and temperature shifts smoothly from one half of the planet to the other. Because Earth's path around the sun is close to a circle, the distance between our planet and our star changes only slightly over the year. So the dominant factor shaping the seasons is not how far we are, but how we are tilted. From the long, low sun of high-latitude winters, casting extended shadows across snow and ice, to the near overhead sun of tropical noons, pouring energy into lush forests and warm oceans. The changing angle of sunlight and the length of day create bands of climate across the globe. In these ways, the combination of tilt and orbit transforms a simple flow of solar energy into a complex mosaic of climate zones, from equatorial rainbelts to polar deserts. These seasonal cycles are not just a backdrop. They are an engine that drives Earth's living systems. In spring, increasing light and warmth trigger plant growth. From temperate forests leafing out to microscopic phytoplankton blooming in the oceans, capturing energy from the sun and feeding entire food webs. Animals respond as well, with birds undertaking long migrations between breeding and feeding grounds, whales following shifting blooms of plankton and krill, and countless species timing reproduction to peaks in food availability. Weather patterns, including monsoon rains, storm tracks, and jet streams, are guided by the contrast between warming and cooling regions, weaving a dynamic but broadly predictable environment that organisms have adapted to over millions of years. Underlying this apparent stability is another subtle guardian: the Moon. Earth's large companion, born from a colossal impact early in the formation of our solar system, helps to steady our axial tilt through its gravitational pull. Without the Moon, simulations suggest that Earth's axis might wander chaotically over long timescales, swinging between extreme tilts that could plunge one pole into near-permanent daylight while the other endures long darkness, disrupting climate zones and challenging the continuity of ecosystems. The relative steadiness we enjoy is, in part, a testament to the dynamic and transformative processes of the cosmos that placed a stabilizing satellite in our sky. Yet even this graceful cycle of seasons is not truly permanent. Over deep time, subtle shifts in Earth's orbit and tilt, driven by the complex interplay of gravity within the solar system, have nudged our climate between ice ages and warmer intervals, reshaping coastlines, ecosystems, and the very conditions for life. Join us as we embark on a journey into these longer, slower rhythms, where the familiar pattern of spring and autumn becomes just one chapter in a far grander climate story that is still unfolding around us. Across Earth's long history, the climate has not simply shifted between mild ice ages and gentle warm periods. It has swung to extremes that seem almost alien compared to the world we know. From global glaciers to tropical polar seas, our planet has explored a vast range of possible states while still remaining a cradle for life as we know it. One of the most dramatic episodes is known as Snowball Earth, a time hundreds of millions of years ago when geological evidence suggests that ice sheets may have reached nearly to the equator. Ancient rocks in Africa, Australia, and South America, now sitting in warm latitudes, preserve glacial scratches and deposits that formed when those regions were closer to the tropics, implying that entire oceans may have been sealed beneath thick ice, and that bright reflective snow dominated most of the planet's surface. This kind of deep freeze is linked to powerful feedbacks in the climate system, especially ice albedo amplification, where expanding ice reflects more sunlight, which cools the surface further, which grows even more ice. In these ways, a modest initial cooling, perhaps from changes in the sun's output or continental positions, can be amplified by the planet itself into a runaway freeze, until Earth resembles a white, glittering sphere drifting through the universe, its usual blue oceans hidden from view. Yet even this extreme state did not last forever, because the same geological forces that shape continents also help regulate climate over millions of years. Volcanic eruptions continued beneath the ice, adding carbon dioxide to the atmosphere while weathering of rocks, which normally removes CO2, slowed almost to a halt under the frozen surface. Over vast spans of time, greenhouse gases built up, trapping more of the sun's energy until the ice began to melt back and the oceans reappeared, a testament to the dynamic and transformative processes of the cosmos operating even on our seemingly quiet planet. In striking contrast, other intervals in Earth's past were dominated by intense greenhouse warmth, when there was little or no permanent ice anywhere on the surface, and the polar regions hosted forests, swamps, and diverse ecosystems. During parts of the Cretaceous period, for example, crocodile-like reptiles and lush vegetation lived within the Arctic Circle, and the temperature difference from equator to pole was far smaller than it is today, giving the planet a more uniformly warm, humid character. From snowball Earth to tropical poles, these extremes reveal that our world is not a static backdrop, but a restless, evolving system, shaped by the slow exchange of carbon between rocks, oceans, atmosphere, and the deep interior. Join us as we embark on a journey through this deep time perspective, which shows that, despite wild swings, Earth has remained within bounds that keep liquid water stable and allow complex life to emerge, and which will guide us in the next part of our story toward understanding how this long-term stability might fare in the face of rapid changes driven by a single species. That stability across deep time sets the stage for another, equally remarkable story. The story of life itself slowly unfolding on this planet. From the perspective of the wider universe, where galaxies collide and stars burn through their fuel in brilliant arcs, the emergence of living cells in a thin film of water on a small rocky world is a testament to the dynamic and transformative processes of the cosmos. Life on Earth appears to reach back more than 3.5 billion years into an oceanic world very different from the one we see today. The young planet, still reshaped by impacts and volcanic activity, hosted warm, mineral-rich waters in which simple, single-celled organisms took hold. These early microbes, tiny compared with the planets and stars that dominate our usual sense of scale, were nonetheless profound, because in their chemistry we see the first hints of the complex webs that would one day support forests, animals, and ultimately life as we know it. For most of Earth's history, however, the living world was almost entirely microscopic, a hidden biosphere of bacteria and archaea occupying oceans, sediments, and thin films of moisture on rocks. There were no trees to catch the wind, no animals to walk on land, and no birds to trace patterns beneath the galaxies wheeling overhead. From tiny cells to vast microbial mats, life remained close to the water's surface, quietly transforming the chemistry of the oceans and atmosphere long before any large organism left an imprint visible to the unaided eye. One of the pivotal innovations was photosynthesis, the ability of certain microbes to capture sunlight and use its energy to build organic molecules. Over hundreds of millions of years, their activity released oxygen as a byproduct, and this gradual accumulation led to what we call the Great Oxygenation Event, when the atmosphere shifted from almost no free oxygen to levels that could support new metabolic pathways. In these ways, microscopic organisms reshaped the entire planet, altering ocean chemistry, enabling the formation of an ozone layer and laying the groundwork for more complex cells. From this transformed environment emerged eukaryotic cells with internal compartments and nuclei, and eventually multicellular organisms, which could grow larger, specialize their tissues, and explore new habitats. Only in the last few 100 million years did complex life move decisively onto land, with the rise of rooted plants, sprawling forests, insects, and vertebrates walking under the sun. Compared to the long ages ruled by microbes, these familiar ecosystems occupy only a thin outer layer of Earth's timeline, much like the thin shell of the biosphere that clings to its surface today. Our own species appears in just the final moments of this narrative, a brief flicker when set against billions of years of microbial innovation and planetary transformation. Join us as we embark on a journey further into this layered history, where we will see how these ancient biological revolutions interact with Earth's physical systems, and how understanding that interplay can help us think about the future habitability of our home and of other planets scattered throughout the wonders of the cosmos. The universe is a massive place filled with countless wonders and mysteries, yet the air quietly filling our lungs is one of its most surprising stories. Join us as we embark on a journey not outward to distant galaxies and stars, but inward into the invisible ocean of gas that makes Earth uniquely habitable among the planets of our solar system. Early in Earth's history, the atmosphere was profoundly different from the one we experience today. There was almost no free oxygen, and instead the air and oceans were dominated by gases like carbon dioxide, methane, and nitrogen, shaped by volcanic outgassing and the chemistry of a still cooling world. In these ways, our planet resembled many other rocky planets we observe, a world where the first microbial communities relied on alternative metabolic pathways, using chemical gradients, dissolved iron, or sulfur compounds as their sources of energy rather than oxygen. Over time, a remarkable innovation appeared among tiny aquatic organisms. Cyanobacteria, microscopic architects of planetary change, evolved a new form of photosynthesis. These cells used water and sunlight to capture carbon dioxide and, as an unintended consequence, released molecular oxygen as a waste product. At first, this oxygen reacted immediately with surrounding materials in the oceans, oxidizing dissolved iron and other reduced elements, but slowly, atom by atom, it began to alter the chemistry of Earth's surface and skies. This slow accumulation led to one of the most dramatic transitions in our planet's history, known as the Great Oxygenation Event. As oxygen levels rose, vast amounts of iron in the oceans rusted out, settling onto the seafloor and forming the banded iron formations we now mine on land, a geological record of atmospheric transformation. For many anaerobic organisms adapted to an oxygen-poor world, this new gas was toxic, damaging their cellular machinery and driving widespread ecological upheaval and probable mass extinctions. What was waste for one lineage became a powerful, disruptive force for nearly all the rest. Yet oxygen's reactive nature also opened an entirely new energetic pathway. Once it began to accumulate in the atmosphere and oceans beyond the capacity of rocks and seawater to absorb it, life could evolve metabolic systems that used oxygen directly, extracting far more energy from food molecules than anaerobic pathways allowed. This higher energy yield made possible larger, more complex cells and eventually multicellular organisms whose tissues, organs, and behaviors depend on continuous, efficient energy flow. In these ways, oxygen paved the path toward animals, toward forests breathing in rhythm with the skies, and toward life as we know it on this small world, orbiting an ordinary star. Every breath we take today, every heartbeat supported by oxygen-rich blood, is a testament to the dynamic and transformative processes of the cosmos, expressed through ancient microbes that reshaped a planet. As we look ahead to the next chapter, we will explore how this oxygenated atmosphere, combined with Earth's internal heat, plate tectonics, and protective magnetic field, weaves together a stable yet fragile system that keeps our home world habitable and offers a guide for recognizing living planets elsewhere among the wonders of the cosmos. That stability, however, has never meant stillness, and when we step back across the full sweep of geological time, we find that Earth's history is punctuated by a few brief, tumultuous intervals when the tapestry of life is abruptly torn and rewoven. Join us as we embark on a journey into these mass extinctions, relatively short episodes on the geological timescale when a large fraction of species vanish from the fossil record, leaving behind thin, haunting boundaries in the rocks that circle our planet like quiet memorials. A mass extinction in this sense is not just a gradual fading, but a rapid pruning of the tree of life, a global crisis in which ecosystems on land and in the oceans lose most of their branches in what may be only hundreds of thousands or even tens of thousands of years. From tiny microbes in the sea to large animals on the continents, entire ways of making a living can disappear. And yet, in these ways, the underlying physical planet continues to turn, its continents still drifting, its interior still convecting, its orbit still guided by the gravity of the sun at the heart of our solar system. One of the most dramatic examples is the end Permian extinction about 252 million years ago, when more than 80 to 90% of marine species and a majority of land species were lost, an event so severe it is sometimes called the Great Dying. Evidence points to immense volcanic eruptions in what is now Siberia, releasing vast amounts of carbon dioxide and other gases, which warmed the climate, altered ocean chemistry, and may have stripped oxygen from deep waters, turning large regions of the sea into hostile, low-energy environments where complex life could not easily persist. Another, more familiar crisis is the end Cretaceous event 66 million years ago, marked worldwide by a thin layer rich in the element iridium, rare in Earth's crust but common in some asteroids. Here, a large impact in what is now the Yucatan Peninsula appears to have worked together with volcanism and climate shifts, triggering wildfires, blocking sunlight, disrupting food webs, and ultimately wiping out all non-avian dinosaurs, while small, adaptable mammals and birds survive to inherit newly opened ecological spaces. In each case, the causes differ: massive volcanism, asteroid impacts, rapid climate change, and shifts in ocean circulation or chemistry. But the pattern is similar, with Earth's interconnected systems pushed beyond familiar limits, and then, slowly, recovering. After the Great Dying, new groups of marine reptiles and modern corals appeared. After the end, Cretaceous, mammals radiated into niches once held by large reptiles, and flowering plants and insects diversified together, a testament to the dynamic and transformative processes of the cosmos playing out on a single world. Mass extinctions then act as reset buttons, erasing certain branches of life as we know it, while allowing surviving lineages to experiment, diversify, and reshape ecosystems, from forests to shallow seas, in ways that would otherwise have been unlikely. Today, we see signs that human activities are increasing extinction rates through habitat change, climate warming, and altered chemistry of the atmosphere and oceans. Yet even here, Earth reminds us of both resilience and vulnerability. Resilience because over millions of years, life tends to return and diversify. Vulnerability because the particular communities, species, and stable climate that support our own civilization are not guaranteed to reappear. As we move forward, we will explore how understanding these past upheavals can guide our choices, helping us preserve the delicate, thin biosphere that clings to Earth's surface, while we continue to search for living planets elsewhere among the wonders of the cosmos. In all of this vast history, from molten beginnings to repeated cycles of ice and fire, the appearance of our own species occupies only the thinnest edge of the record. Join us as we embark on a journey in time, where we compress Earth's 4.5 billion year story into a single day. A 24-hour clock that lets us see just how recent we truly are. On this clock, Earth forms from a swirling cloud of dust and rock in the early solar system around midnight, while the first simple cells appear before 4 a.m., and complex multicellular life does not arrive until about 9 p.m. Dinosaurs stride across the continents sometime after 10:30 p.m., only to vanish a little before 11 p.m. And for most of the remaining hour, mammals and evolving ecosystems quietly fill in the empty niches. Modern humans, our own species, emerge in roughly the last 30 seconds before midnight, and all of recorded history, from the first cities to spaceflight, fits into a fraction of a second. Yet, in that brief flicker, we have become a new kind of geological force. In just a few thousand years, we have cut into mountains, diverted rivers, and reshaped coastlines, building vast agricultural plains, dense cities, and global networks of roads, dams, and harbours that rival natural processes in their scale. From tiny farms to megacities that glow at night, our patterns of settlement and technology are written into the surface of the planet as clearly as ancient lava flows or the scars of past impacts. Scientists now use a single word to capture this extraordinary influence: Anthropocene, a proposed new epoch in Earth's geological timeline defined by human activity. The Anthropocene is marked by fossil fuel combustion and the rapid rise of greenhouse gases, by plastic particles and industrial metals preserved in sediments, and by accelerating losses of biodiversity as habitats are fragmented or transformed. In these ways, our species has woven itself into the deep cycles of carbon, nitrogen, and water that once changed only over tens of thousands or millions of years. Our tools and choices now interact directly with Earth's climate engine, its circulating atmosphere and oceans, its ice sheets and forests, often pushing these systems to adjust faster than they naturally would. From the chemistry of the upper air to the acidity of the oceans, from groundwater depletion to the retreat of glaciers, the signals of our presence are spreading across the globe, a testament to the dynamic and transformative processes of the cosmos operating through a single technological species on a small world. To understand our future, though, we must look not only at what we are doing to Earth, but also at what Earth, and the changing sun that illuminates it, will do in return, as the star at the heart of our solar system slowly evolves and reshapes the conditions for life as we know it. The universe is not only vast in space, it is vast in time, and our small, warm world occupies just one chapter in a much longer stellar story. Join us as we embark on a journey into that deep future, where the quiet evolution of our star slowly rewrites the rules for life as we know it. The Sun, a medium-sized yellow dwarf star at the heart of our solar system, is not static. It is a nuclear engine whose internal balance is changing with every passing second. In its core, hydrogen nuclei are fused into helium, releasing immense amounts of energy that stream outward as light and heat. As this fusion proceeds, helium ash accumulates. The core contracts under gravity, and the surrounding layers respond by heating up and burning hydrogen more rapidly. In these ways, stars like the Sun gradually increase their luminosity over billions of years, brightening even as they appear unchanging to us on human timescales. When Earth first formed from the swirling debris of the protoplanetary cloud, the young Sun shone more dimly than it does today, perhaps about 70% as bright. Over 4.5 billion years, that output has crept upward, altering the balance between incoming solar energy and the infrared radiation Earth emits back into space. Our atmosphere, oceans, and even the slow work of plate tectonics have helped maintain a relatively stable climate despite this brightening, a testament to the dynamic and transformative processes of the cosmos expressed through our planet's own internal cycles. Yet this stabilizing act cannot continue forever. Models of stellar evolution suggest that in roughly 1 to 1.5 billion years, the Sun's luminosity will be high enough that Earth's surface will receive significantly more energy than today. As temperatures rise, more water will evaporate, strengthening the greenhouse effect, which in turn drives further warming in a self-reinforcing loop. At a certain threshold, this can tip into a runaway greenhouse state, where the oceans gradually evaporate into the atmosphere and are ultimately broken apart and lost to space. In that future, our blue planet would become a far drier world, its surface likely inhospitable to complex multicellular life, long before the Sun swells into a red giant and threatens to engulf the inner planets entirely. This perspective introduces the idea of a habitable window, a finite span of time when conditions on a planet allow stable liquid water and rich biospheres at the surface. Earth may already be past the exact midpoint of its most clement era, residing in a slowly narrowing band of comfort set by the evolving Sun. Rather than prompting urgency or alarm, this realization can deepen our quiet appreciation of the present, reminding us that we live during a particularly gentle interval in a much larger cosmic sequence. As we look ahead to the Sun's later stages, we also prepare to explore how Earth itself will continue to change, and how future intelligence might respond to a brightening sky and a shifting home. As we consider this gentle interval in the Sun's life, we are reminded that not all planets bathe in such a balanced light, and that even within our own solar system, the line between comfort and catastrophe can be astonishingly thin. Join us as we embark on a journey to our nearest planetary neighbor, Venus, to see what happens when that balance is lost. Venus, often called Earth's sister world because it is so similar in size and basic composition, is today one of the most hostile planets we know. Its atmosphere is almost entirely carbon dioxide, wrapped in global clouds of sulfuric acid that hide the surface from view. At ground level, the pressure is about 90 times that of Earth's sea level, comparable to being nearly a kilometre under the ocean, and temperatures hover around 470 degrees Celsius, hot enough to melt lead and to sterilize any known form of life as we know it. The reason for these extreme conditions lies in a process called the runaway greenhouse effect, a kind of feedback loop in which warming feeds on itself. On a planet with surface water, as temperature rises, more water evaporates into the air, and water vapor is a powerful greenhouse gas that traps additional heat. This extra trapped energy causes further warming, which drives still more evaporation, and in these ways the cycle accelerates, pushing the climate toward a new, far hotter state. On Earth, under present conditions, several interconnected systems keep us far from this Venus-like outcome. Our abundant oceans act as vast heat and carbon reservoirs. Our dynamic clouds reflect a significant portion of incoming solar energy back to space. And our carbon cycle, driven in part by plate tectonics and weathering of rocks, gradually locks carbon dioxide away in minerals. The result is a climate that has wandered over deep time, yet has remained stable enough for liquid water, complex ecosystems, and the long unfolding of life as we know it. However, models of planetary climate and stellar evolution suggest that such stability cannot last forever. As the sun slowly brightens over hundreds of millions to billions of years, there is a threshold beyond which Earth's oceans will begin to evaporate more rapidly than they can cool the surface. Once that point is crossed, water vapor could accumulate to the point that a moist or runaway greenhouse takes hold, the seas begin to boil, and water molecules high in the atmosphere are broken apart by sunlight, allowing hydrogen to escape to space and leaving our world desiccated. Seen from this perspective, the difference between Earth and Venus is not an unbridgeable gulf, but a narrow window in temperature, pressure, and radiation, a testament to the dynamic and transformative processes of the cosmos. We might quietly ask ourselves how differently we would treat our planet if we could truly feel how thin that window is, and how precious it may be to future generations who look up at the same bright star, wondering how long their home can remain so uniquely blue. To feel how narrow that window really is, it helps to see Earth in context, not as an isolated oasis, but as one member of a larger planetary family orbiting our star. Join us as we embark on a journey outward from the sun, tracing the sequence of worlds that share our solar system, and noticing, step by step, what they have and what they lack. We begin with Mercury, the closest planet to the Sun, a small rocky sphere only about a third the width of Earth, locked in an environment of intense solar energy and extreme temperature swings. With almost no atmosphere, its airless surface is heavily cratered, resembling our moon, and daytime heat can soar while nighttime cold plunges hundreds of degrees in the opposite direction, a stark demonstration of what happens when rock faces space without a protective, gaseous blanket. Next comes Venus, similar to Earth in size and composition, yet transformed into something profoundly different by its atmosphere. Venus is wrapped in a dense cloak of carbon dioxide with clouds of sulfuric acid, creating a runaway greenhouse effect that drives surface temperatures hot enough to melt lead and pressures comparable to the deep ocean on Earth. In these ways, Venus shows us that two planets of similar bulk and orbit can diverge dramatically, depending on how their atmospheres evolve. Our own world follows, then beyond it, Mars orbits as a smaller, colder cousin, its thin atmosphere unable to retain much heat. The Martian surface is a landscape of dusty deserts, giant volcanoes and vast canyons, with polar caps of ice and clear evidence that liquid water once flowed in rivers and pooled in lakes. Today, that water is mostly locked as ice or hidden underground, leaving Mars dry and frigid, yet still one of the most intriguing places to search for traces of past life as we know it. Farther out, the solar system transitions from rocky bodies to giants dominated by gas and ice. Jupiter, the largest of the planets, is an immense sphere of hydrogen and helium, with no solid surface in the usual sense, its deep atmosphere carved by powerful jet streams and storms, including the Great Red Spot, a tempest larger than Earth. Saturn, slightly smaller but adorned with its famous rings, shares this gaseous nature and hosts a rich system of moons, some icy, some geologically active, each shaped by gravity and tidal forces. Beyond them, Uranus and Neptune, the ice giants, contain more water, ammonia, and methane in their interiors, giving Neptune its deep blue hue and Uranus its pale, tilted mystery. Their atmospheres are cold and windswept, with storms and high-speed winds, and they too are orbited by moons and faint rings, extending the diversity of our planetary neighborhood. Among these moons, worlds like Jupiter's Europa and Saturn's Enceladus likely hide subsurface oceans beneath shells of ice, warmed by tidal flexing and internal heat. These hidden seas may be potential habitats, yet even here, there is no open sky, no continents and global oceans under a breathable atmosphere, no stable, temperate climate spread across a sunlit surface. Earth alone combines liquid surface water, a protective atmosphere, active geology, and long-term climate stability in a way that seems unusually welcoming for complex life. Seen against this backdrop, our planet is not the center of the universe, but it is a remarkably comfortable niche within a varied system of planets and moons, each a testament to the dynamic and transformative processes of the cosmos. As we continue outward to the realm of smaller, icy bodies and, eventually, to the vast structures of galaxies beyond our sun, we carry with us this growing sense that our blue world is both ordinary in its origins and extraordinary in its habitability, a balance we are only beginning to understand. From the familiar comfort of our blue world, it is easy to forget how small our home really is in the vast architecture of the universe. Yet there is one image captured from the frontier of our own solar system that brings this contrast into sharp, quiet focus and invites us to see Earth with new eyes. In 1990, as Voyager 1 was leaving the planetary realm behind, engineers sent a simple but profound command: turn the camera around. The spacecraft, a robotic explorer, already more than 6 billion kilometers from the Sun, pivoted its instruments back toward the inner solar system and took a family portrait of the planets. Within that mosaic, there is a single frame that has become iconic, a small rectangle of scattered light and darkness in which our entire world is reduced to almost nothing. In that photograph, Earth appears as a tiny, faint speck, less than a pixel in size, suspended in a broad, diagonal beam of sunlight scattered inside the camera's optics. The surrounding space is mostly black, with soft bands of color crossing the field, so that our planet seems to float in a cosmic sunbeam, fragile and almost accidental, yet precisely where it must be. From this distance, there are no continents, no oceans, no signs of cities or clouds. Only a point of light, barely distinguishable from the background. Carl Sagan, who had advocated for this final look homeward, reflected on the image in words that continue to resonate. He reminded us that every human being who has ever lived, every culture, every language, every teacher and student, Every explorer and farmer and child, every act of kindness and cruelty, every empire and revolution has unfolded on that minuscule stage. In these ways, the pale blue dot becomes more than a photograph. It is a condensed history of life as we know it, held within a single shimmering point. The image confronts us with a gentle paradox. On the one hand, Earth is clearly insignificant on a cosmic scale, a dust mote adrift in the vast dark between the stars. One small planet orbiting an ordinary star in a galaxy of hundreds of billions of stars. On the other hand, for us, it is everything. The only place where oceans fill basins, where air and gravity cradle our bodies, where the intricate web of organisms and climates and continents has given rise to conscious minds that can contemplate the wonders of the cosmos. It is, for now, the only known cradle of life. Join us as we embark on a journey even farther outward, beyond Voyager's vantage point, where our entire solar system shrinks to a spark among the Milky Way's countless stars, and where Earth's apparent insignificance only deepens the mystery of how unique it may truly be. From the perspective of interstellar space, our entire solar system becomes a small, luminous structure embedded within something far grander. The Milky Way galaxy, our vast stellar city in the universe. The Milky Way, a barred spiral galaxy, is a rotating disk of hundreds of billions of stars, immense gas clouds, and an even larger halo of invisible dark matter, all bound together by gravity into a flattened, slowly turning whirlpool of light and structure. In this immense system, the Sun, a medium-sized star with its family of planets, does not sit at the center, but orbits around the galactic core, much as Earth orbits the Sun. Our solar system circles the Milky Way's center at roughly 220 kilometers per second, tracing a nearly circular path through the galactic disk. At that speed, it still takes on the order of 225 to 250 million years to complete a single circuit, a galactic year. So every time Earth finishes one such orbit, the face of our planet, its continents, climates, and the forms of life as we know it have been utterly reshaped. We do not travel along this path from a crowded downtown, but from a relatively quiet suburb. The Sun resides in the Orion Arm, sometimes called the Orion Spur, a minor spiral arm located between two larger, brighter arms of the galaxy. This region is populated by stars, nebulae, and clusters, yet it is far less dense and tumultuous than the central bulge, where stars are packed more closely and energetic events are more common. In these ways, our stellar neighborhood offers a balance between access to the raw materials of star and planet formation and a measure of distance from the most hazardous environments. That distance matters. Near the galactic center, frequent supernova explosions, intense radiation fields, and the influence of the central supermassive black hole can bathe nearby systems in high-energy particles and disruptive bursts of energy. By contrast, our position in the Orion Arm appears comparatively gentle, with fewer nearby supernovae and a reduced likelihood of catastrophic radiation events that could strip atmospheres or sterilize planetary surfaces. Our calm orbit, far from perfect yet relatively stable over billions of years, may have given Earth the long, continuous window it needed to maintain liquid water, preserve its atmosphere, and allow complex ecosystems to emerge. Our planet's habitability, then, is not only a story of oceans, air, and plate tectonics, but also of where the Sun happened to form within the Milky Way's grand design. a testament to the dynamic and transformative processes of the cosmos. Join us as we embark on a journey still farther outward to see how the Milky Way itself fits into a web of galaxies, and how even our galaxy's environment subtly shapes the past and future of our fragile home world. As we step beyond the familiar spiral of the Milky Way, we enter a realm where our home galaxy becomes just one island of stars among an almost unimaginable multitude. The observable universe, the portion of the cosmos from which light has had time to reach us, may contain hundreds of billions of galaxies, each with its own stars, planets, and potential stories of formation and change. The Milky Way itself, a barred spiral galaxy with hundreds of billions of stars, resides in a small gravitational community known as the local group. This collection includes our nearest large neighbor, the Andromeda Galaxy, another majestic spiral on a slow-motion collision course with us, as well as dozens of smaller dwarf galaxies that orbit like scattered companions. From these few dozen systems to the immense clusters and filaments that thread the cosmos, gravity weaves galaxies into a vast, three-dimensional web. On still larger scales, many local groups gather into clusters and superclusters, linked by filaments of galaxies that span hundreds of millions of light years, with great cosmic voids in between. From tiny dust grains in a molecular cloud to these continental-sized structures of galaxies, the universe organizes itself through gravity and time, a testament to the dynamic and transformative processes of the cosmos. In these ways, our Milky Way is both ordinary, as one galaxy among many, and extraordinary, as the specific environment in which our solar system and Earth have taken shape. Over the past few decades, as we have surveyed other stars, we have discovered that planets are common companions, not rare exceptions. Thousands of exoplanets now populate our catalogues, from hot Jupiters skimming their stars to rocky worlds in wider orbits, suggesting that the basic process of planet formation unfolds throughout galaxies. Yet, among all these discoveries, we still have no confirmed twin of Earth, no world with the same gentle balance of temperature, liquid water, protective atmosphere, magnetic field, and long-term stability. This uncertainty opens a profound question. Habitable planets may be widespread, with countless opportunities for life as we know it, or they may be rare oases in a largely hostile universe. Either way, at this moment in our exploration, Earth remains the only known world that actually hosts life, the only place where oceans, air, rocks, and biology intertwine into a single self-sustaining system. Here, it can be helpful to pause. While we imagine clusters and filaments stretching across billions of light years, almost everything you have ever known unfolds within a thin shell around a small planet circling an ordinary star. Join us as we embark on a journey that will soon turn back toward this intimate scale, to examine Earth not just as a point in space, but as a complex, evolving system whose future is deeply connected to its cosmic surroundings. From the perspective of the vast universe, our solar system is just one faint point among billions. Yet even within this modest neighborhood, one world would quietly demand attention. If a distant civilization swept their instruments across our star and its family of planets, Earth would not be the largest, the hottest, or the coldest, but it would be the strangest. They might begin, as we do, with light. By splitting starlight that has passed through a planet's atmosphere, astronomers obtain a spectrum, a kind of chemical fingerprint that reveals what gases are present. In such a survey, Mercury would appear essentially airless. Venus would show thick carbon dioxide and clouds of sulfuric acid, and Mars would hint at a thin, cold envelope of carbon dioxide with only traces of anything else. Earth, however, would display strong signatures of oxygen and water vapor together, a combination that is difficult to maintain without some continuous source of renewal. Oxygen, on its own, is chemically reactive and tends to bind with rocks and surface materials, so a stable, oxygen-rich atmosphere suggests an active process replenishing it. On Earth, that process is photosynthesis carried out by plants, algae, and microbes, which also anchors the delicate balance of gases that supports life as we know it. If our hypothetical observers noticed oxygen coexisting with methane, a gas that is quickly destroyed in such an oxidizing environment, they would see an even stronger clue. These two gases together are in chemical disequilibrium and must be constantly supplied, a classic biosignature. They could also watch our planet change with the seasons. As continents tilt toward and away from the sun, the amount of green vegetation waxes and wanes, subtly altering the color and brightness of Earth over the course of a year. This red edge of chlorophyll, a sharp increase in reflectivity at certain wavelengths, would rise and fall in a regular rhythm, hinting at vast, light-harvesting organisms carpeting the surface. In these ways, the global biosphere would reveal itself as a dynamic, planet-wide process. Beyond biology, there would be techno-signatures. Sensitive radio telescopes might detect narrow-band, artificial radio emissions leaking from our communications and radar systems, unlike the broad, natural signals from stars and galaxies. High-resolution imaging of the night side could reveal scattered points and webs of light that brighten and dim with local time, consistent with electrically powered cities. Even the composition of our atmosphere, with rising levels of industrial pollutants and unusual molecules, might whisper of an industrial civilization reshaping its world. Set against this, the other planets would seem comparatively quiet. Venus's thick clouds would be reflective but monotonous, driven by a slow, global circulation rather than rapid, localized weather. Mars's thin air would show dust storms and polar caps, yet little sign of abundant liquid water. The gas giants would glow with reflected sunlight and deep storms, but lack the sharp spectral markers of surface oceans and continents. Earth's atmosphere, by contrast, would appear vibrant and changeable, its bright, reflective clouds swirling over blue oceans and varied land, a testament to the dynamic and transformative processes of the cosmos acting on a small, rocky world. If we first encountered Earth as a distant exoplanet suspended as a pale point of light around an ordinary star, we might speak of it with the same quiet wonder we reserve for the most promising worlds in other galaxies. Join us as we embark on a journey, in the next part, to look back at our home with this outsider's eye, and to ask what its past and future might look like when seen from such a cosmic distance. From that distant vantage point where Earth is only a pale point of light, we now move closer and discover that this world is not a simple, solid sphere, but a living tapestry of interacting parts. The planet beneath our feet, the air we breathe, the water that flows and freezes and evaporates, all belong to a single integrated whole that scientists call the Earth system. The Earth system is composed of several major spheres, each with its own character yet never truly separate. The atmosphere, a thin envelope of gases surrounding the planet; the hydrosphere, all liquid water from the deepest oceans to tiny droplets in clouds; the geosphere, the rocky interior and crust shaped by plate tectonics and volcanic activity; the cryosphere, the realms of ice and snow from polar caps to mountain glaciers; and the biosphere, the fragile film of life as we know it that occupies a surprisingly narrow band of height and depth. From microscopic organisms in the soil to forests and oceans, this biosphere is woven through all the others. These spheres interact continuously over timescales that range from moments to millions of years. Warm ocean waters in the tropics, for example, release vast amounts of heat and moisture into the atmosphere, helping to drive global circulation patterns that transport energy from the equator toward the poles. In these ways, changes in sea surface temperature can alter the paths and strengths of jet streams, influence the development of hurricanes, and even shift rainfall belts on distant continents. A subtle change in the Pacific Ocean can echo through the atmosphere and bring floods to one region while causing drought in another. Life itself participates in this web of feedbacks. Vegetation on land pulls carbon dioxide from the atmosphere through photosynthesis, storing some of it in wood, roots, and soils, and thereby helping to regulate the greenhouse effect that keeps the planet warm enough for oceans to remain liquid. Forests and grasslands also modify the reflectivity, or albedo, of Earth's surface. Dark, dense canopies absorb more sunlight than bright snowfields or deserts, altering how much solar energy is retained. Through transpiration, plants move water from the ground into the air, feeding cloud formation and influencing local and regional climate. Disturbances in one part of the system can propagate in complex and sometimes delayed ways. When ice in the cryosphere melts, for instance, sea level rises, and the exposed darker ocean absorbs more sunlight, which can accelerate warming and further ice loss. Deforestation in the tropics reduces carbon uptake, raises surface temperatures, and can weaken regional rainfall, which in turn affects river systems, soil stability, and the habitats of countless species. Each of these changes, in turn, can feed back into the atmosphere and oceans, subtly reshaping patterns of wind, temperature, and precipitation. Seeing Earth as a single dynamic system reveals both its resilience and its sensitivity. Over billions of years, feedbacks among rocks, water, air, ice, and life have helped keep surface conditions within the narrow range that allows complex organisms to flourish, a testament to the dynamic and transformative processes of the cosmos operating on a planetary scale. Yet this same interconnectedness means that rapid disturbances can ripple outward, pushing the system toward new states that may be less favorable for the intricate web of species that now exists. As we continue our journey, we will explore how this finely balanced system came to be, and how it might respond to the changes we are now introducing, intentionally or not, from within. The finely balanced system at Earth's surface rests on foundations that are anything but simple, extending downward into realms that are almost entirely hidden from direct view. Join us as we embark on a journey away from the familiar blue skies and sunlit continents, and into the dark, pressurized domains that occupy most of our planet's volume and a vast fraction of its surface. The deep ocean, stretching from the twilight zone down into the abyssal plains and trenches, is a vast, dark realm that covers more than 2/3 of Earth's surface, yet receives no sunlight at all. From a few hundred meters down to more than 11 kilometers in the deepest trenches, pressures rise to hundreds or even thousands of times what we experience at sea level, while temperatures hover just above freezing, creating an environment that would crush and chill unprotected land organisms instantly. In these ways, the deep sea is as alien to us as the surfaces of distant planets, yet it lies only a few kilometers below the waves we see every day. Within this darkness, however, there are oases of intense activity where the interior of the solid Earth meets the ocean. Along mid-ocean ridges and certain seafloor fractures, hydrothermal vents, essentially hot springs on the ocean floor, spew mineral-rich, superheated water into the surrounding cold depths. Here, instead of relying on sunlight, entire ecosystems are powered by chemosynthesis, a process in which microbes use chemical energy from compounds like hydrogen sulfide, drawn from Earth's interior, to build organic molecules. Around these microbes gather dense communities of tube worms, clams, and other organisms, demonstrating that life as we know it can be sustained not only by starlight, but also by the hidden energy flowing outward from our planet's hot interior. Beneath the oceanic and continental crusts, the solid Earth continues downward for thousands of kilometers, forming the mantle and core regions that are even less accessible than the deepest trenches. We cannot drill more than a tiny fraction of the way down, so our understanding of these layers comes indirectly through seismic waves from earthquakes, high-pressure laboratory experiments, and sophisticated numerical models that simulate rock behavior under immense temperature and gravity. The mantle, though solid on short timescales, slowly convects like an extremely viscous fluid, transporting heat from the deep interior toward the surface, while the liquid outer core, rich in iron, generates Earth's magnetic field, a protective shield that deflects charged particles from the sun and helps preserve our atmosphere within the wider universe. These hidden regions are not passive backdrops. They are active engines driving plate tectonics, mountain building, volcanism, and the long-term cycling of carbon and nutrients that help stabilize climate over millions of years. In these ways, the deep ocean and deep interior together regulate surface conditions, influencing everything from ocean chemistry to the habitability of continents, a testament to the dynamic and transformative processes of the cosmos operating beneath our feet. Yet, despite centuries of study, we have mapped other planets and even some moons more completely than our own seafloor, and our picture of the mantle and core remains a kind of carefully constrained shadow. As we continue, we will turn to how this partially known interior shaped Earth's formation and early history, and to the surprising evidence that the story of our home planet is still far from fully written. The universe is a massive place filled with countless wonders and mysteries, yet for us, everything that matters unfolds within a surprisingly thin envelope of air and cloud wrapped around our planet. From the deep mantle below our feet to the heights of the upper atmosphere, Earth's habitability depends on layers we rarely see, but on which we rely every moment. Join us as we embark on a journey upward, leaving the solid surface and passing through the atmosphere, this invisible ocean of gas that shields and moderates life as we know it. High above the weather, in the stratosphere, lies the ozone layer, a region enriched in a molecule made of 3 oxygen atoms. Ozone is fragile and rare, yet it performs a vital task. It absorbs most of the sun's harmful ultraviolet radiation, especially the energetic UVB and UVC wavelengths, that can break chemical bonds in DNA and damage biological tissues. In these ways, this diffuse veil of gas acts like planetary sunscreen, allowing complex ecosystems to flourish on land. Below the ozone layer, we encounter clouds, the visible expression of water vapor, condensing as warm air rises and cools. Clouds, from thin cirrus streaks to towering thunderheads, play a double role in Earth's energy balance. Their bright tops reflect a significant fraction of incoming sunlight back to space, cooling the surface while at the same time their droplets and ice crystals absorb and re-emit infrared radiation rising from the ground, trapping heat that would otherwise escape. A low, thick marine cloud deck over an ocean can cool the underlying water, while high, wispy clouds may have a net warming effect, and together they form a constantly shifting thermostat. Mixed through these layers are aerosols, tiny solid or liquid particles suspended in the air. Volcanic ash, desert dust, sea salt, smoke from fires, and human-made pollution all contribute to this fine haze. Some aerosols are highly reflective and brighten clouds or scatter sunlight directly, tending to cool the planet. Others, such as black carbon from soot, absorb energy and warm the air around them. Their lifetimes are short compared with greenhouse gases, yet a large volcanic eruption or sustained pollution can alter regional and even global climate for years. At this point, it helps to pause and interrupt our usual picture of the sky as empty blue above our heads. Instead, we can think of it as a multi-layered dynamic shield and thermostat, where ozone filters ultraviolet light, clouds juggle incoming solar energy and outgoing infrared glow, and aerosols fine-tune how much radiation is reflected or absorbed. Interwoven with these components are greenhouse gases such as carbon dioxide, methane, and water vapor, which allow visible light from the sun to reach the surface while impeding the escape of heat, maintaining temperatures that keep liquid water stable over much of the globe. From tiny aerosol particles to vast storm systems that span continents, this coupled system of gases, clouds, and radiation is a testament to the dynamic and transformative processes of the cosmos, expressed on a planetary scale. It is delicately balanced. Without greenhouse gases, Earth would be a frozen world. With too many, it would resemble Venus, a planet where surface temperatures can melt lead. Our position in the solar system, at just the right distance from the sun, only becomes truly habitable because these atmospheric layers collaborate with gravity and incoming energy to keep our world neither too hot nor too cold. As we continue, we will move from this protective shell back down to the surface, exploring how oceans, ice, and living organisms interact with the atmosphere to create the long-term climate story of our home planet, and how that story may change in the future. Yet even this familiar surface with its oceans, ice, and living organisms rests on a razor's edge of conditions that could easily have been very different. The universe is a massive place filled with countless wonders and mysteries, but when we look closely at Earth, we see that our own world is one of the most delicate wonder of the cosmos. From the steady glow of our star to the reflective clouds that drift above us, small shifts in key variables can send global temperatures moving in surprising ways. The Sun, a medium-sized yellow dwarf star, varies in its energy output by only fractions of a percent over its cycles. Yet, a sustained change of just 1% in solar brightness would, over time, be enough to push climate zones poleward or equatorward, altering rainfall, ice cover, and the very boundaries of where life as we know it can thrive. Likewise, a modest increase in greenhouse gases, measured in mere parts per million, can trap additional heat, while a change of a few percent in planetary albedo, the fraction of sunlight Earth reflects, can tip the balance between expanding ice and melting seas. Hidden within these gradual trends are climate tipping points, thresholds where slow change gives way to abrupt transformation. Large ice sheets, for example, do not simply melt in a smooth, linear way. Once they retreat beyond certain grounding lines, the loss can accelerate, committing future generations to meters of sea level rise. Ocean circulation, driven by temperature and salinity, can reorganize when enough fresh water enters the North Atlantic, disrupting weather patterns across entire continents. In these ways, the Earth system behaves like a set of interlocked switches, where crossing one boundary can flip others and reshape ecosystems on a planetary scale. We can see how sensitive such systems are by comparing Earth with its neighbours in the solar system. Venus, similar in size and original composition to our planet, likely began with liquid water, yet a runaway greenhouse effect, amplified by thick clouds and intense solar energy, transformed it into a world of crushing pressure and surface temperatures hot enough to melt lead. Mars, smaller and cooler, may once have had rivers and seas, but with weaker gravity and a fading magnetic field, it lost most of its atmosphere to space, leaving behind a thin, cold envelope and frozen deserts. These three planets started from the same protoplanetary cloud, yet feedbacks and small initial differences sent them down radically different paths, a testament to the dynamic and transformative processes of the cosmos. Earth does possess stabilizing mechanisms, such as the slow carbon silicate cycle tied to plate tectonics, which draws carbon dioxide into rocks and releases it again over millions of years, helping to moderate climate as the sun brightens. Biological processes, from forests to marine plankton, further regulate gases and reflectivity. However, these planetary buffers operate on timescales far longer than human lifetimes, and they can be overwhelmed by rapid, concentrated disturbances, like the sudden injection of greenhouse gases that would normally accumulate over geological ages. Join us as we embark on a journey of perspective and imagine, far across our galaxy, the discovery of an exact Earth twin, orbiting a similar star at just the right distance, with the same fragile mixture of oceans, ice, and air. To distant observers, our planet would be such a rare point of blue light. Considering how carefully we would study and protect that distant world, we can begin to ask how this perspective might change the way we treat our own home, as we continue deeper into Earth's long-term story and its possible futures. From that imagined distant blue point, it is natural to ask what it would truly mean for another world to be a second Earth, not just in appearance, but in substance and behavior across deep time. Join us as we embark on a journey from our familiar solar system to the broader universe of exoplanets, where astronomers quietly search for an Earth 2.0 among the countless planets that circle other stars. When scientists speak of an Earth twin, they mean more than a roughly similar world. They mean a planet with almost the same radius and mass as Earth, built from the same rocky materials, orbiting at a comparable distance from a sun-like star, where the balance of starlight and gravity allows liquid water to pool into long-lived oceans. Such a planet would likely need an atmosphere rich in nitrogen, with a modest amount of carbon dioxide and water vapor, perhaps with oxygen or other gases produced by geological or biological processes, creating surface pressures and temperatures that could support life as we know it. To find such worlds, we rely on subtle changes in starlight and gentle tugs of gravity that reveal planets we cannot yet see directly. The transit method, or transit photometry, watches for tiny periodic dips in a star's brightness as a planet passes in front of it, yielding the planet's size and orbital period. The radial velocity technique measures the star's slight back and forth motion induced by the planet's gravity, and from this we infer the planet's mass. When these methods are combined, they give us density, a clue to whether a planet is rocky or gaseous, and spectroscopy of the starlight filtering through a planet's atmosphere can hint at molecules like water vapor, methane, or oxygen. Even if we discovered a planet with Earth's size, mass, orbit, and a seemingly familiar atmosphere, deeper layers of similarity would still be uncertain. Plate tectonics, the slow drift and collision of rigid plates on a mobile mantle, regulates Earth's long-term climate and recycles carbon between rocks, oceans, and air. Without it, a world might freeze solid or enter a runaway greenhouse. A strong magnetic field powered by a liquid metal core shields our atmosphere from the energetic particles streaming from its star, preserving water and air over billions of years. Biological evolution, once it begins, can reshape the atmosphere and surface in unpredictable ways, so that two Earth-like planets might host very different skies and ecosystems. We can imagine standing on such a distant twin, feeling a familiar pull of gravity underfoot, watching clouds build and dissolve in patterns that resemble our own weather, and perhaps seeing a yellow-white star trace a path across the sky that looks much like our sun's. The rocks beneath our feet might be basalt and granite, the oceans salted and restless, yet the constellations overhead would be unknown, and every living thing, if life existed there at all, would carry a separate history, a distinct experiment in chemistry and adaptation. In these ways, even a true twin would not erase the singularity of our own world, but would instead highlight how much of Earth's story arises from specific, contingent events. For now, Earth remains the only confirmed planet where oceans endure, continents drift, and a biosphere transforms the air, a testament to the dynamic and transformative processes of the cosmos. As we continue, we turn back from imagined twins to our one confirmed example, using Earth itself as our most detailed laboratory for understanding habitability, stability, and the long-term future of life on a small world orbiting an ordinary star. From this vantage point, Earth is not only a planet of drifting continents and persistent oceans, but also a world where one species has become a noticeable participant in the planet's own systems. As we continue, we do not step outside the universe's calm logic of cause and effect. Instead, we trace how our choices, technologies, and patterns of living now interact with the same flows of energy and matter that have always shaped this small world in the solar system. One of the clearest connections lies in the thin layer of gases surrounding us, the atmosphere that makes life, as we know it, possible. When we burn fossil fuels, clear forests, and carry out industrial processes such as cement production, we release additional greenhouse gases including carbon dioxide, methane, and nitrous oxide. These molecules, though present in trace amounts, influence the radiative balance of the planet, absorbing and re-emitting infrared energy that would otherwise escape to space. In these ways, human activity gently adjusts a control knob that has always existed, altering the balance between incoming solar radiation and outgoing heat. On the surface itself, our use of land changes how Earth reflects and redistributes sunlight and water. Forests, croplands, cities, and bare soil each have different albedo, the fraction of solar energy they reflect back towards space, and different patterns of evapotranspiration, the combined evaporation from soil and water, and the release of water vapor from plants. When we replace dense, dark forests with lighter agricultural fields, or with heat-absorbing urban areas, we reshape local and regional climates by modifying how much energy is absorbed, how moisture cycles through the air, and how carbon is stored in vegetation and soils. These changes do not rival the scale of galaxies or stars, yet they matter deeply within the delicate shell where weather and climate unfold. Water, too, carries our signature. Nutrient runoff from agriculture, wastewater, and atmospheric deposition delivers excess nitrogen and phosphorus to rivers, lakes, and coastal oceans. In many regions, this stimulates intense blooms of algae, which eventually die and decompose, consuming dissolved oxygen and creating low oxygen or anoxic dead zones, where many forms of marine life struggle to survive. Over time, such inputs can shift entire marine and freshwater ecosystems, favoring some species over others, and subtly reorganizing food webs that have developed over long spans of geological time. All of these influences are superimposed on the natural variability that has always characterized Earth's climate and biosphere, from volcanic eruptions and solar cycles to slow orbital shifts that redistribute sunlight over tens of thousands of years. Untangling the human contribution from this background is a careful scientific task, much like separating overlapping signals from distant stars within a crowded region of the galaxy. Yet it is also an opportunity. By understanding the combined pattern, we learn how to live more gently within Earth's established systems, aligning our activities with the long rhythms of this planet, so that future sections of our story can explore not only what has changed, but how we might guide those changes toward a stable, enduring home. The pattern of change we now observe invites a deeper question. How much can this planet absorb and still remain the familiar world that shaped us? From tiny microbes in the soil to vast belts of clouds circling the globe, Earth behaves as a woven system, and every strand has some capacity to bend before it breaks. In the language of Earth system science, resilience is a system's ability to absorb disturbances and still maintain its basic structure and function. A resilient forest, for example, can endure storms, insect outbreaks, and occasional fires, yet continue cycling water, storing carbon, and providing habitat. The same idea scales upward from local landscapes to the entire planet, where flows of energy, matter, and gravity link atmosphere, oceans, rocks, and life into a single, intricate whole. We can see this resilience in action. After a wildfire, a temperate forest may look devastated, but within months, shoots emerge from the ash, seeds germinate in the opened light, and over years to decades, the canopy closes again. Coral reefs, battered by bleaching when ocean temperatures rise, sometimes recover when cooler waters return and local conditions improve, rebuilding their elaborate structures that shelter fish and invertebrates. In these ways, ecosystems demonstrate that disturbance is not always destruction. It can be a catalyst for renewal, a testament to the dynamic and transformative processes of the cosmos written here on Earth. Yet every resilient system has limits. Push a forest too often with hotter, more frequent fires, and trees may be replaced by grasslands or shrublands. Warm and acidify the oceans beyond certain thresholds, and coral reefs may shift to algae-dominated states that no longer support the same abundance of life as we know it. When these shifts occur, the system does not vanish, but it settles into a new configuration, with different rules and different possibilities. To understand such limits on a planetary scale, researchers have proposed the idea of planetary boundaries, a framework that identifies safe operating spaces for humanity within key Earth system processes. These include the stability of the climate, the integrity of the biosphere, the cycles of carbon, nitrogen and phosphorus, the chemistry of the oceans, and the condition of land, fresh water, and the protective ozone layer high above us. From the formation of our solar system's rocky planets to the emergence of complex biospheres, similar thresholds likely shaped worlds around distant stars and galaxies. If we cross too many of these boundaries, Earth will not cease to orbit the Sun, and life in some form will almost certainly persist. But the planet may move into states less favorable for human societies. Coastlines could redraw themselves, weather patterns could reorganize, and the thin shell of the biosphere that clings to this world could host a different cast of species. Join us as we embark on a journey into these possible futures, where our choices in the coming centuries will influence not only human stories, but the very conditions under which future life experiences Earth, and where the next chapter asks how far along these paths we have already travelled. In thinking about Earth's future, it helps to stretch our sense of time far beyond a human lifespan, and even beyond the rise and fall of civilizations, until centuries, millennia, and eons begin to feel like chapters in a single, continuous story. From the near future of our own descendants to the distant ages when continents themselves will migrate, Earth remains our home, shaped by both human choice and the deep forces of the universe. In the next few centuries to a few thousand years, the dominant influence on climate and ecosystems will be us, our energy systems, our land use, and our technology. The carbon we release, the forests we cut or restore, and the way we design cities and agriculture will determine how much the average temperature rises, how high the seas climb, and which species thrive or vanish. In these ways, the thin shell of the biosphere, already only a fragile coat of paint on a vast planet, will respond to decisions made within just a handful of human generations. Stretching our view to hundreds of thousands of years, the pulse of ice ages driven by subtle shifts in Earth's orbit and tilt would normally continue to modulate climate, bringing cycles of glaciation and retreat. Yet large, long-lived greenhouse gas emissions could delay or even suppress these natural cycles, leaving future ice sheets smaller or absent, and rewriting the pattern of coastlines and ecosystems that would otherwise unfold under the slow rhythm of gravity and sunlight. On timescales of millions of years, human structures erode, languages vanish, and most traces of our present societies are buried or transformed, while Earth's own tectonic engine continues to rearrange the surface. Continents drift a few centimeters per year, but over 10 or 50 million years, this motion opens and closes oceans, raises new mountain ranges, and alters ocean circulation patterns that carry heat around the planet. The Himalaya will weather down as other ranges rise. Seaways may open where land exists today, and the climate will respond as carbon is locked into rocks or released by volcanism, a testament to the dynamic and transformative processes of the cosmos acting within a single planet. If we move forward to hundreds of millions of years, the map of Earth becomes almost unrecognizable. Numerical models suggest that the current continents may merge into a new supercontinent, perhaps forming near the equator or over one of the poles, changing wind patterns, rainfall, and the distribution of deserts and forests. Ocean basins could close, subducting familiar seafloor back into the mantle, while new crust forms elsewhere, and the biosphere adapts to a world with different coastlines, different mountain chains, and perhaps entirely new groups of dominant species. Then, at the scale of 1 billion years and beyond, the story is increasingly governed by the evolution of the Sun itself. As the Sun, a main sequence star in our solar system, slowly brightens, the extra energy reaching Earth will likely push our planet out of the comfortable zone for liquid surface water, even if we manage our atmosphere perfectly. Over hundreds of millions to 1 billion years, oceans may gradually evaporate, water vapor will amplify heating, and the familiar conditions that support life as we know it on the surface will fade. From tiny microbes in deep rocks to complex organisms in oceans and on land, the biosphere will contract into extreme niches until eventually surface habitability ends. This layered view from centuries to billions of years acts as a quiet pattern interrupt in how we usually think about the future, shifting us from immediate crises toward a broader appreciation of Earth as part of the wonders of the cosmos. Our choices in the near term matter profoundly for ourselves and for many generations to come. Yet they unfold within a planetary story that began in a collapsing cloud of gas and dust and will continue long after our present era. Join us as we embark on a journey into that larger context, where the next section turns from distant scenarios back to the question of how well we truly understand the Earth system we are already changing. When we look up from our changing Earth and imagine the wider universe, it is natural to wonder whether our long-term future might unfold somewhere else, on other planets or in artificial worlds of our own design. From tiny space stations to visions of vast orbital habitats, we are beginning to explore what it would mean to carry the conditions for life, as we know it, beyond the thin shell of air that now protects us. Join us as we embark on a journey away from the surface and then back again to see what that really entails. Engineers and scientists have outlined a range of possibilities, from rotating space habitats that use centrifugal force to mimic gravity, to permanent bases on the Moon, to colonies on Mars, the small, cold planet that shares our solar system with Earth. Each of these concepts must solve the same fundamental challenges, providing breathable air, stable water supplies, reliable gravity-like forces for our bodies, and shielding from radiation that streams through space from the Sun and distant galaxies. What our atmosphere and magnetic field do automatically, without our conscious awareness, would have to be recreated by layers of metal, plastic, ice, and carefully monitored machines. In orbit or on the lunar surface, there is no protective blanket of air tens of kilometers thick, and no global magnetic field like Earth's to deflect high-energy particles. So every habitat becomes a carefully sealed bubble. On Mars, the situation is only slightly more forgiving. There is some atmosphere, but it is thin and cold, and the planet's weaker gravity and lack of a strong magnetic field mean that cosmic radiation still reaches the surface with ease. In these ways, environments beyond Earth are harsh and unforgiving, requiring constant engineering attention simply to approximate the conditions that our planet's formation and internal energy provide continuously and quietly. Even if we succeed in building such outposts for a long time, they are likely to depend heavily on Earth for advanced materials, complex components, scientific expertise, and the cultural continuity that makes a human community more than a collection of survival systems. A Mars settlement might grow its own food in pressurized greenhouses and recycle water with great efficiency, yet still rely on Earth-based industries for replacement electronics, medical equipment, and the knowledge base that keeps its technology functioning. The blue planet would remain the deep reservoir of resources and information upon which these distant experiments in habitation draw. There is also the psychological and emotional dimension of leaving the only world where our species evolved, where every recorded story, tradition, and landscape of meaning has taken shape. To live on a world with a red sky or inside a rotating cylinder in deep space would be to experience a constant reminder that we are far from the familiar rhythms of Earth's days, seasons, oceans, and living ecosystems. In this sense, off-world habitats would stand as a testament to the dynamic and transformative processes of the cosmos, and to our adaptability, but also to our ongoing connection to the planet that first made that adaptability possible. From tiny spacecraft to imagined Martian cities, our attempts to escape Earth's surface reveal not a prison we must flee, but the extraordinary rarity of a world that already does, effortlessly, what we struggle to reproduce with all our technology. As we contemplate these future journeys, it becomes ever clearer that Earth is a life-supporting oasis in a vast, mostly hostile universe, and that understanding and preserving this oasis may be the most important part of any path we take among the stars. Seen from the surface, Earth can feel vast, solid, and endlessly familiar. Yet from a different vantage point, it becomes something else entirely. Join us as we embark on a journey away from the ground beneath our feet, to look back at our home the way only a few hundred human beings have ever truly seen it. Astronauts who have orbited our planet or traveled to the moon and back often report a profound psychological shift known as the overview effect, a cognitive change in which our usual boundaries and divisions fall away, replaced by an almost overwhelming sense of unity, fragility, and interconnectedness. The Earth, a dynamic world that formed from the violent collisions of dust and rock in the early solar system, is suddenly perceived not as a collection of countries and conflicts, but as a single, living oasis suspended in the vast darkness of the universe. From space, the visual impression is both simple and deeply striking. Our planet appears as a bright, delicately marbled sphere, wrapped in a thin veil of atmosphere that, from orbit, looks like a faint blue line tracing the curve of the world. There are no visible borders or nations, only continents, oceans, clouds, and the subtle gradients of color that hint at deserts, forests, and ice. Against the black backdrop, punctuated only by distant stars and the faint glow of the Milky Way, Earth floats like a small, illuminated vessel moving through an endless cosmic sea. For many who witness this directly, priorities begin to reorder themselves. From this altitude, the political and social divisions that dominate our daily lives seem to shrink. while shared vulnerabilities become impossible to ignore. The thin atmosphere that shields us from harmful solar energy, the magnetic field generated deep within the planet that deflects the solar wind, and the narrow temperature range that allows liquid water to persist, all appear as finely balanced conditions that sustain life as we know it. In these ways, the overview effect can act as a quiet but powerful reminder that preserving this balance is more fundamental than any disagreement that plays out on the surface. Most of us will never ride a rocket through gravity's pull to see this view directly, but we can still approximate its impact. High-resolution images from the International Space Station, time-lapse videos of city lights and auroras, immersive simulations, and even simple contemplative imagination allow us to rehearse this shift in perspective, to picture ourselves looking back at the whole Earth at once. As we cultivate this habit of seeing the planet as a single, evolving system, we move gently toward what some call planetary consciousness, an awareness that we are not separate from Earth but expressions of it, intertwined with its oceans, atmosphere, rocks, and biosphere. This emerging perspective will guide us as we explore how Earth's many systems interact, and how this intricate web has kept our world habitable for billions of years, a testament to the dynamic and transformative processes of the cosmos. This global planetary consciousness becomes most real not in distant theories, but in the quiet details of our daily lives. From the moment we wake and take a breath to the simple act of standing on the ground, we are immersed in Earth's systems, often without noticing how extraordinary these ordinary moments truly are. Join us as we embark on a journey not across galaxies or between stars, but into a single breath of air. When we inhale, we draw in molecules of nitrogen, oxygen, and trace gases that have been circulating through the atmosphere for billions of years. Some of the oxygen in our lungs was once part of ocean water, lifted into the sky by the sun's energy, split by ancient microbes, and released by forests and plankton. A few of the carbon dioxide molecules we exhale may have passed through dinosaur lungs, dissolved in long-vanished seas, or been locked for ages in carbonate rocks before returning to the air. In these ways, each breath is a moving archive of Earth's history, a record of exchanges between oceans, rocks, plants, and animals. The thin layer of air we depend on, only a few tens of kilometers thick compared to Earth's radius, is constantly stirred by winds, storms, and subtle waves of pressure. Yet to us, breathing feels effortless and still, a quiet partnership between our bodies and the atmosphere that makes life as we know it possible. Consider the wind brushing against our skin. What feels like a gentle caress is actually the large-scale flow of air driven by uneven solar heating, Earth's rotation, and the shape of continents and oceans. From tiny eddies between city buildings to jet streams circling the globe, this motion transports heat, moisture, and even microscopic life. A passing cloud overhead, white and calm, is a three-dimensional structure of countless droplets and ice crystals, condensed from water that may have once been locked in polar ice or flowed through ancient rivers. On a clear night, when we look up at the stars, we are gazing through this same protective envelope. The atmosphere filters harmful radiation, and the magnetosphere, generated by Earth's liquid outer core, deflects much of the solar wind, preventing the atmosphere from being stripped away. The quiet we feel under the night sky exists because these invisible shields, have held for billions of years, a testament to the dynamic and transformative processes of the cosmos. Even a glass of water or a handful of soil holds this cosmic story. The water contains hydrogen forged in the early universe and oxygen made in ancient stars, combined on a young Earth and cycled ever since through clouds, rain, rivers, and living cells. The soil beneath our feet is ground rock mixed with the remains of countless organisms, shaped by plate tectonics, weather, and roots. As we continue, we will move from these intimate sensations back to the broader engines that keep Earth habitable, tracing how all of these simple experiences emerge from planetary-scale processes. From these simple sensations of soil, water, and air, we can gently lift our perspective outward and see how remarkably balanced our entire planet is. The universe is a massive place filled with countless wonders and mysteries, yet here on this small world, a very specific set of conditions aligns to allow life as we know it to unfold in quiet continuity. Earth orbits the Sun at just the right distance, in a region often called the habitable zone, where temperatures allow liquid water to persist on the surface. The Sun, a medium-sized yellow star, provides a steady flow of energy, neither too intense nor too faint, and our nearly circular orbit keeps that energy relatively constant over the course of a year. From the frozen edges of the outer solar system to the scorched inner orbits of other planets, this gentle stability stands out. Around us, the atmosphere forms a thin, protective shell, only a tiny fraction of Earth's radius, yet essential in these ways. It traps heat enough to prevent a global deep freeze, filters harmful radiation, and carries clouds and storms that move water and energy around the globe. Above that, an invisible magnetic field, generated by the motion of liquid metal in Earth's outer core, reaches tens of thousands of kilometers into space, deflecting much of the solar wind and helping to prevent our atmosphere from being stripped away, as appears to have happened on Mars. On the surface, liquid water flows in oceans, rivers, and groundwater systems, dissolving minerals, transporting nutrients, and providing a medium where complex chemistry can proceed. Beneath our feet, plate tectonics slowly reshapes continents and seafloor, recycling crust and regulating long-term climate through the carbon silicate cycle. This restless geology, a testament to the dynamic and transformative processes of the cosmos, helps keep Earth's climate within bounds that complex ecosystems can endure for billions of years. All of this supports a rich biosphere, a thin, delicate film of life extending only a few kilometers above and below the surface, yet transforming the entire face of the planet. Over deep time, organisms have altered the atmosphere, soils, and even rocks, weaving themselves into every part of the Earth system. Join us as we embark on a journey through this perspective. A world that appears ordinary from afar, yet is intricately tuned up close. None of these features appeared all at once. They emerged from long chains of events and physical laws, from the collapse of a cold molecular cloud that formed our solar system, to violent planetary collisions that built Earth and its moon, to the slow cooling of the interior and the onset of plate motion. In other planetary systems, many of these ingredients may exist separately, yet, as far as we currently know, the exact combination we experience here is unique. In these ways, Earth is both a small, ordinary planet orbiting an unremarkable star in one galaxy among billions, and an irreplaceable home for us, the only place where our particular branch of life as we know it has taken root. How we respond to that awareness, whether with care, curiosity, or indifference, becomes part of Earth's unfolding story. And in the next moments, we will quietly explore what that response might mean. We have traced Earth from a small, ordinary planet to an irreplaceable home, and now we can gently turn that vast story inward toward our own lives resting on its surface. Join us as we embark on a journey that folds cosmic time into the span of a single lifetime, linking the formation of atoms in distant stars to the quiet rhythm of your breathing right now. The atoms in your body, from the calcium in your bones to the iron in your blood, were forged in ancient stars that ended their lives in supernova explosions, a testament to the dynamic and transformative processes of the cosmos. Those atoms drifted through interstellar space, part of a cold molecular cloud, until gravity gathered them into the nebula that formed our solar system, and eventually into the rocks, oceans, air, and living cells of Earth. In these ways, every heartbeat is connected to galaxies and to the long chain of stellar births and deaths that made life as we know it possible. From that immense history, our daily experience can seem very small, yet it is still real and meaningful. Each choice we make, whether we walk instead of drive, listen carefully to another person, or pause to notice a tree outside our window, becomes a tiny thread woven into Earth's ongoing story. Most of us will never see a galaxy through a large telescope or watch a star's formation directly, but we participate in the same universe of matter and energy each time we share warmth, grow food, or simply feel the pull of gravity holding us to the ground. Caring about our surroundings is one of the most direct ways we interact with the larger Earth system. When we protect a local wetland, plant a small garden, or support clean air in our cities, we are quietly adjusting the flows of water, carbon, and nutrients that link atmosphere, ocean, soil, and living organisms. A neighborhood park, a patch of forest, or a stretch of coastline might seem modest compared to planets and stars, yet these places are where the biosphere, climate, and human communities meet. Stewardship in this light need not feel like a burden or an emergency alarm, but rather a natural response to understanding the rarity and beauty of our home world. From tiny microbes in the soil to the thin blue atmosphere that shields us from space, Earth has maintained conditions for liquid water and complex life for billions of years, and our awareness of this can gently guide our actions toward care instead of neglect. As this perspective settles, you can allow it to follow you into rest, into dreams, and into the quiet moments of waking life that lie ahead. The same universe that formed galaxies and stars also formed you, here on this planet, at this time, and in the closing moments of our journey, we will reflect on what it means to simply exist as a conscious part of Earth's unfolding story. As we let that perspective rest in our minds, we can gently turn back and trace the path we have followed together, a quiet arc that began far beyond our own skies. The universe, with its countless galaxies and stars, was our starting point, and from that almost unimaginable scale we slowly narrowed our focus, moving from vast clusters of galaxies to our spiral Milky Way, to the modest arm where our solar system orbits, and finally down to this single world beneath your feet. Join us as we embark on a journey in memory, returning to those early moments when our home first took shape. We recalled how the solar system emerged from a cold, rotating cloud of gas and dust, and how, within that cloud, gravity drew material together into the young sun and a disk of forming planets. In these ways, Earth began as stardust and fragments, as repeated collisions and mergers, its surface once molten and hostile, yet already a testament to the dynamic and transformative processes of the cosmos. From that fiery beginning, we watched Earth differentiate into layers, a dense metallic core, a flowing mantle, and a solid crust that would one day carry oceans and continents. The liquid outer core, moving slowly under immense pressure, generated a magnetic field that extends tens of thousands of kilometers into space, shielding the atmosphere from the charged particles streaming outward from the sun. Around this protected globe, gases accumulated into an atmosphere, water condensed into oceans, and a thin, fragile surface became capable of supporting life as we know it. We then explored Earth as an interconnected system where no part truly acts alone. The climate, driven by sunlight and internal energy, interacts with the oceans that store heat and move it around the planet. Rocks rise in mountain ranges and are worn down by wind and rain, their minerals carried to the sea, while plate tectonics slowly recycles the crust and helps regulate carbon over millions of years. Above and within this shifting geology, the biosphere, that thin shell only a few kilometers thick, responds to these changes and, in turn, alters the air, the water, and even the rocks themselves. Across deep time, we trace the long arc of life, from simple cells in ancient seas to complex ecosystems on land, through extinctions and renewals that reshaped the face of the planet. Eventually, a recent arrival appeared. Humans, conscious beings able to understand gravity, stars and planets, yet also able to alter climate, landscapes, and the delicate balances that sustain us. We have become a new force within the Earth system, capable of harm, but also of care, reflection, and choice. As this quiet recap settles in, you can allow your awareness to soften, knowing that whether you are drifting into sleep or simply resting, you are held by a planet that has supported life for billions of years. The same processes that shaped continents and oceans now cradle you in this moment, under an atmosphere and a sky that are the long, patient work of the universe itself. And in the next part of our journey, we will turn more gently toward what it means to belong to such a world. In this quiet moment, as we remain still on the surface of our world, the motion around us continues with a scale and smoothness that can be difficult to feel, yet is always present. The Earth, a dynamic planet shaped by billions of years of formation and change, is rotating on its axis, orbiting the Sun, and journeying with the entire solar system through the Milky Way, all at immense speeds that our senses do not directly register. From tiny particles in the air around us to the grand sweep of galaxies, we are carried effortlessly through the universe. Even as you lie down, perhaps with your eyes closed, the ground beneath you is turning at hundreds of meters per second. The planet is circling the Sun at about 30 kilometers every second, and the solar system itself is moving around the center of our galaxy, drawn onward by gravity and the combined mass of countless stars. All of this motion layered together means that you are traveling through space at well over 1 million miles per hour. Yet your experience is one of rest, of stillness, of being gently held by this planet that has made life as we know it possible. We can carry that awareness as a soft kind of companionship, a reminder that we are part of a vast, ongoing story that began long before us and will continue long after. Join us as we embark on a journey not of distance now, but of attention, turning inward to the simple, steady connections that tie us to the larger Earth system. The sunrise that slowly colors the sky, the pattern of clouds drifting overhead, the feeling of rain on skin or wind moving through leaves, are all expressions of the same flows of energy and matter that shape climates, carve landscapes, and support the thin, delicate biosphere where almost all known life resides. In these ways, very ordinary experiences become quiet doorways back to a planetary perspective. To notice a shadow moving as the Earth turns, to feel temperature change with a setting sun, or to listen to distant thunder is to sense, in a small but real way, the processes that make this world habitable. Each moment of curiosity, however brief and unhurried, is a testament to the dynamic and transformative processes of the cosmos that gathered gas and dust into a star, arranged planets around it, and eventually produced oceans, continents, and living beings capable of wondering about it all. As you drift towards sleep or move gently into whatever comes next, you might choose to keep a light thread of that curiosity with you, learning more about our planet, our solar system, and the wider universe at whatever pace feels natural. There is no need to rush. The same patient forces that shaped mountains and guided galaxies have time to accompany your questions. For now, it is enough to know that in all this cosmic vastness, Earth is, for the moment, our only home. And that is a beautiful place to rest your thoughts. Wherever you are and however you listen, may you find a quiet sense of belonging on this moving world we share.